Edge AI depends on hardware that can run models close to where data is produced, so speed, power use, and size all matter. The hardware choices in this chapter shape what devices can actually deploy AI at the edge. Signal type is the first hardware decision in Edge AI because the model can only work with the data the device can capture cleanly and affordably. A useful edge system begins by turning a real-world event into data that still carries enough detail to support a decision. Power, bandwidth, memory, and latency all limit how much of that signal can survive the trip into model. Inputs at the edge come from two places: measurements from the physical world and digital signals already produced by another system. Temperature, vibration, light, or distance are sensor readings, while logs, packet traces, and control messages are already digital. The important question is how each input must be sampled, time-stamped, filtered, and compressed before it can drive a local decision. The form of the signal changes the whole design, because time series, audio, images, and video all place different demands on the hardware. Most edge sensors produce a time series, but the timing can differ a lot. Some streams arrive on a fixed schedule, some only when something changes, and some report a windowed summary instead of a raw sample. Exact timestamps matter because downstream logic needs to know when each change really happened. A daily environmental reading and a high-rate vibration stream are both time series, but they live at very different scales. Once the sample rate rises, storage, transmission, and compute start to dominate, so the system may need filtering or local feature extraction before inference. Audio behaves like a time series, but it is demanding because it often runs continuously and at high sample rates. Raw waveforms usually get processed into features or cleaned with signal processing first, so the model sees something smaller and more informative than the raw stream. Images are grids of values, so resolution and channel count directly affect memory and bandwidth. Video adds a frame stream on top of that, which means the system has to manage both spatial detail and temporal continuity at the same time. These signal properties define the workload before any model runs. If the sensor is poorly calibrated, the range is too narrow, or the environment distorts the measurement, the edge device may be processing unreliable data from the start. Once the signal becomes numbers, the way those numbers are represented starts to shape memory use, precision, and compute cost. A float 32 value keeps more detail than an int 8 value, but it also uses more memory and may be slower to move or process. On constrained hardware, that trade-off can decide whether the whole pipeline fits locally. The device has to move, store, and transform the measurement efficiently, so encoding is not a late implementation detail. Downsampling or quantizing early can help, but only if the task can still see the pattern it needs. The best way to group edge workloads is by modality, because the signal form predicts the timing, memory, and processing limits that matter most. Modality is more useful than the sensor label on the box. It tells you whether the device cares most about cadence, continuous acquisition, buffering, frame rate, or bandwidth, and that points directly to the right hardware features. A modality table is a quick map from input shape to design pressure. It helps you compare very different devices using the same lens, which makes the hardware choices easier to reason about. A concrete system makes the differences easier to see because the same modality ideas play out very differently in a real device. Riverwatch node mostly handles small time series readings, so it can sleep for long stretches and wake only to sample or respond. When something unusual happens, it sends a short event instead of pushing a full stream upstream. And that works because the input stays structured and compact. A wake-word device has to keep listening all the time, so latency and signal processing become central concerns. A low-light camera pushes a different kind of load. Image detail, exposure, channels, and frame buffering all raise memory pressure much more than the river node does. Hardware choice starts with the shape and volume of the signal, because those two things determine what can run comfortably on device. An engineer has to estimate how often data arrives, how each sample is encoded, and how much must be kept before inference. A product team is really asking whether the signal can be captured cleanly, stored cheaply, and processed fast enough on the target board. The model comes later. First comes the signal form, because once you can recognize time series, audio, image, and video, the reason for different devices and memory sizes becomes clear. Visual sensing turns a scene into data that a machine can reason about. The point here is not just the camera itself, but how image, light, and depth signals become useful evidence for an edge system. A camera is not merely collecting a picture. It is sampling many points across a scene and packaging them into a form software can process. That matters because the real challenge is rarely one measurement. It is handling many measurements at once, while the lighting, motion, and power conditions keep changing. An image becomes much easier to work with when you think of it as a grid of measure values. That view makes resolution and channels feel like design choices, not just camera specifications. Resolution tells you how finely the scene is sampled, so higher resolution usually means smaller objects and edges are easier to detect. Channels add another layer, because grayscale and color images carry different amounts of information, and that directly affects memory, bandwidth, and processing load. That spatial layout is exactly what vision models use. Instead of treating every pixel like an independent reading, the model can learn local patterns and larger structures, which is why images work so well for detection, occupancy, anomaly spotting, and scene understanding. Time changes the problem. Once frames arrive in sequence, the system is no longer reading one snapshot at a time. It is interpreting motion and change. A single frame gives you a static view, but a sequence shows what is happening between frames. That extra temporal layer is useful for tracking behavior and events, yet it also raises the cost in storage, memory movement, pre-processing, and latency. A still image task can tolerate occasional samples, but a video task often needs continuous capture or a short frame history to decide whether something changed. On an edge device, the real question becomes whether the system can keep up with the stream without dropping frames or draining the battery. Visual sensing is broader than ordinary color images. When daylight is weak or the scene is hard to interpret, other sensing modes can carry the visual burden. The important idea is that a system can still understand a scene even when it is not relying on standard RGB light alone. Infrared and depth signals give the device other ways to represent what is in front of it. Infrared extends operation into darkness and low visibility conditions. With an IR light source, the sensor can still form a usable image at night, and that is often a better fix than forcing a model to infer too much from weak visible light data. Depth sensing changes the kind of evidence available to the system. By measuring distance, it can separate foreground from background, estimate range, and make geometry matter more than color when the task needs spatial clarity. So the word visual should be interpreted broadly. A device may use brightness, reflected infrared, depth, or a mix of these signals to represent the scene in front of it. The Riverwatch node makes the trade-offs easier to picture. Once the sensor is aimed at a riverbank, the choice of camera mode directly affects what kinds of events the system can detect. In daylight, a simple camera may be enough to flag movement, spot a large object in the water, or notice a changed shoreline. When conditions get worse, the same node may need infrared illumination so the scene stays readable instead of disappearing into darkness. That small change in sensing mode affects the whole design. Illumination draws power, infrared behavior changes the sensor response, and video capture adds pressure on storage and buffering if the node has to decide what to keep and what to transmit. Good visual system design starts with the sensing setup, not with the model. Resolution, frame rate, and sensing method all shape what the downstream software can realistically do. Higher resolution can help with small objects, but it also increases the amount of data the processor must handle. Faster frame rates capture motion better, yet they can overwhelm a low-power node, and infrared or depth sensing may improve robustness while introducing different costs. The right answer depends on lighting, motion, network access, and energy budget. A riverbank camera, a factory inspection system, and a moving autonomous monitor all face different constraints, so they need different sensor choices. That order is the habit worth keeping. Ask whether the scene is static or dynamic, daylight or night, local or streamed, color or grayscale, and shallow or depth-rich. Those answers often decide whether the project works at all. Visual data is valuable because it carries structure, but that structure costs memory, compute, and power. In edge AI, the sensing hardware is not a side detail. It is one of the main parts of the system's intelligence. Acoustic and vibration sensing starts with the physical signal itself, because edge systems must capture motion in the world before any model can interpret it. The important question here is how that signal enters the device and why the sensor choice shapes everything that follows. The key idea is that sensing happens before machine learning ever sees the data. A device first turns pressure, vibration, or motion into a measurable stream, and only then can local processing classify or detect anything useful. A microphone, hydrophone, or vibration sensor does not understand sound or motion. It measures change in a medium and converts that change into data. That distinction matters because the raw signal becomes the material the model works with later. That makes sensor selection part of the system design, not a detail to fill in afterward. The sensor decides what the device can notice, how accurately it notices it, and which edge workloads are realistic in the first place. These sensors differ in where they are used, but they share a common data shape, a changing signal over time. That shared shape is what lets the same kinds of models and feature extraction methods work across audio, vibration, and ground motion tasks. A microphone measures pressure changes in air, a hydrophone does the same in water, and geophones, or seismometers, track motion in the ground. Industrial vibration sensors extend that idea to machines, where the goal is to observe oscillation in equipment like motors, pumps, and bearings. The important point is that the sensor produces a sequence of values, not a single snapshot. That is why these systems care about patterns over time, whether the task is a wake word, a machine fault, or an unusual acoustic event in the field. A low-power field device like Riverwatch Node shows the design trade-off clearly. Listen continuously, detect a meaningful event, and send only the result. The signal may travel through air, water, or structure, but the real choice is matching the sensor and deployment to the medium and the kind of motion you expect. Frequency range sets the boundary of what the sensor can observe with useful fidelity. If the task needs information outside that range, the model never gets the detail it needs, no matter how good the compute below it is. That range is not just a spec sheet number. It defines the part of the signal the hardware can actually capture well. Once the signal falls outside that usable range, the important structure is gone before any inference starts. A wake-word device needs the speech cues that separate one phrase from background noise, while an industrial monitor may need a narrow vibration band that indicates wear or imbalance. In both cases, the workload has to fit the sensor's response window. Even inside the usable range, sensors may not respond evenly at all frequencies. That can reshape the signal, change what the model learns, and make two devices disagree about the same physical event. Sampling controls how much of the analog signal survives the conversion into digital form. The sample rate has to be high enough for the event of interest, or the system loses the high-frequency detail that makes the pattern recognizable. A sensor may be able to sense a range of motion, but the sampling process decides how much of that motion is preserved accurately. Choose the rate too low, and the digital stream cannot carry the frequencies the task depends on. That is why many edge failures get blamed on the model when the real problem started upstream. If the sensor is too slow, too narrow, or too distorted, no processor can rebuild information that never made into the data stream. Always-on audio works only when a microphone and sampling pipeline are matched to the speech pattern you need to catch. The same logic applies to vibration monitoring and field sensing. The hardware has to fit the motion band and deployment conditions, not a generic idea of sound. Sensor choice is really workload choice, because the hardware determines what kind of signal the rest of the system will ever see. Once the capture stage is fixed, it shapes power use, storage, bandwidth, and the amount of compute needed downstream. The right microphone, hydrophone, geophone, seismometer, or vibration sensor is the one that fits the medium, the frequency range, and the environment. That match prevents wasted compute and avoids forcing the system to compensate for poor capture later. Good hardware selection starts with practical questions about the signal path. What medium carries it? What frequencies matter? How fast a sample? And how much distortion is acceptable? Those answers save power and prevent deployment failures when the device has to run unattended. The durable lesson is that acoustic and vibration sensing succeeds when the sensor, the signal, and the task are aligned. If the capture stage is wrong, every later layer inherits that mistake, so the hardware decision has to be right from the start. Acoustic and vibration sensing starts with motion in a medium and ends with measurable data. The key idea is that tiny physical changes can be turned into signals a machine can analyze. The important shift is from physical movement to a digital signal. Once that shift happens, the hardware has to preserve time, not just intensity. A microphone does not understand speech. It converts pressure changes into samples over time. That time structure matters because the machine is not seeing an image or a table. It is seeing a stream that changes moment by moment. The same sensing idea shows up in air, water, ground, and machinery. Each device is chosen because the medium and the kind of motion are different, even though the output is still a sampled signal. The medium changes the engineering choices, but not the basic sensing principle. That is why the same family of sensors can support very different applications. A microphone fits airborne sound, a hydrophone fits underwater transmission, and a geophone or seismometer fits ground motion. Industrial vibration sensors serve equipment monitoring, where repeated motion can reveal wear, imbalance, or resonance before failure becomes visible. For a low-power river node, the question is not which sensor sounds most familiar, but which one can actually detect the physical change in that environment. The useful signal might be acoustic, vibrational, or mechanical, depending on what is changing near the water or infrastructure. The data has to be read as a sequence because the source itself evolves over time. That time ordering is what makes acoustic and vibration sensing different from static measurements. Pressure waves rise and fall, motors vibrate with changing frequency, and structures flex under load. After digitization, those changes become ordered samples that a model can analyze window by window. Once the signal is treated as a time series, hardware design changes. Buffer size, memory use, and compute timing all depend on how much history the device must hold before it can make a decision. Three hardware limits keep showing up: what frequencies matter, how the sensor responds to them, and how fast the device must sample. Those constraints decide whether the data is usable at all. Different tasks need different frequency bands. Voice, environmental sound, machinery vibration, and structural motion do not occupy the same range. So the sensor has to capture the range that contains the real clue. A sensor may claim a range, but still favor some frequencies over others. If the response distorts the spectrum, a model trained on cleaner data can fail after deployment, which is why calibration matters. Sampling has to be fast enough to preserve the highest useful frequencies without aliasing. Too slow loses information. Too fast wastes data movement, storage, and compute. The practical rule is to start with the signal and work back to the sensor. Medium, frequency range, response behavior, and deployment environment all have to line up before the hardware choice makes sense. A microphone, hydrophone, geophone, seismometer, or vibration sensor only works well when it matches the physical setting. That match drives the processor choice, memory budget, battery life, and pre-processing strategy. The useful skill is turning a vague problem into concrete sensing requirements. When someone asks for anomaly detection near a river, the real questions are what is changing, which frequencies matter, how stable the response must be, and how fast the system must sample. Acoustic and vibration sensing only works well when the hardware matches the motion being measured. Medium, frequency range, sensor response, and sample rate decide whether the system captures meaningful structure or just records noise. Visual sensing is where a real scene becomes data that an edge device can use. The point is not just to capture images, but to choose a sensing setup that the hardware can support and the model can actually process. Light has to pass through optics and be sampled by a sensor before it becomes usable input. That conversion step sets the limits for everything downstream. So the sensing choice shapes the whole pipeline. At the edge, sensing is the first translation from physics into numbers. The real design question is whether the device can afford the right kind of sensing, both in power and in compute, before the processor ever sees the data. A standard image sensor gives you a grid of brightness and color measurements, and that grid is the starting point for most camera-based systems. If that input is noisy or poorly matched to the task, no later model can fully recover the lost information. The lens and the sensor together decide how much of the scene gets projected and sampled. A wide view covers more area but spreads detail thin, while a narrow view concentrates pixels where they matter, which is why different applications need different optics. Several properties interact at the same time. Color and spectral response decide what kind of light the camera can distinguish. Pixel size affects sensitivity and noise. Resolution controls detail, and frame rate controls motion capture, latency, and power use. When daylight disappears, the sensor may need help gathering usable scene information. Infrared illumination paired with an IR-sensitive camera can extend visibility after sunset, but it also adds emitter power, changes the operating profile, and affects the features the model receives. A wildlife camera trap shows why this is bigger than one component. Active light can make darkness visible, but can also alter animal behavior and raise energy cost, so the design has to balance sensing quality, battery life, and deployment ethics. A different sensing strategy becomes useful when full video is more data than the task needs. The key idea is to stop thinking in terms of complete frames and start thinking in terms of change. Event cameras report only changes in brightness, so they avoid sending a complete image when the scene is mostly static. That can cut bandwidth and latency, but the algorithm has to work from a very different signal than ordinary video. That trade-off makes event cameras excellent for fast motion and sparse change, but awkward when the task depends on full visual context. The real question is whether the application benefits from change-only sensing or needs a complete scene representation. Some problems need more than a flat image. Once distance and shape matter, the sensor has to describe the scene in 3 dimensions, not just in color and brightness. Time-of-flight sensors, LiDAR, and radar all add distance information to the scene. That extra measurement matters when the system must estimate shape, obstacle position, clearance, or motion in space. Those sensors are specialized because they have to emit energy, measure returns, and often process depth maps or point clouds afterward. A robot or vehicle may need that complexity for safe navigation, but a flat camera cannot supply the same spatial awareness. Radar becomes attractive when fog, dust, darkness, or long-range detection make optical sensing unreliable. It gives a more abstract signal than a camera, so the processing pipeline has to be designed around that different kind of measurement. The main design rule is simple. The sensor has to fit the device around it. Power, storage, bus bandwidth, and compute capacity all limit what visual hardware can run continuously. A camera can produce more data than the processor can analyze, and a 3D sensor can overwhelm storage or communication links very quickly. The best choice is the one the full system can sustain, not the one with the highest specification on paper. That is why sensor literacy matters in embedded AI and robotics. A bad choice creates latency, battery drain, memory pressure, weak night performance, or a design that becomes too expensive to deploy at scale. The Riverwatch Node example pulls the whole idea together. A daytime monitor may work with a small camera. A night version may need infrared illumination, and a power-limited version may need a more specialized sensing mode to produce the right data in the right amount. That rule is the one to keep. If the sensor does not match the task and the platform, the pipeline pays in power, latency, storage, and complexity long before inference can help. Visual sensing turns a real scene into numbers that an edge device can work with, and that simple shift drives many of the trade-offs in this part. The focus is on how cameras and related sensors shape both what the model sees and what the hardware has to carry. A camera frame is not just an image for a person to look at. It is input data for the pipeline. More pixels give more detail, but they also increase memory traffic, bandwidth, compute, and power, which matters immediately on constrained hardware. The first step is to understand how a sensor turns light into a grid of values. Once that conversion is clear, the later trade-offs in color, resolution, and low-light performance make much more sense. An image sensor samples light across the chip and packages those measurements as a numerical array. Grayscale gives one intensity per pixel, while RGB carries multiple channels, which can help recognition but also increases data volume and processing load. Those sensor properties change both image quality and system cost. Pixel size affects low light capture, resolution controls spatial detail, frame rate sets how quickly the scene updates, and spectral response decides which wavelengths the sensor can actually use. The lens and sensor have to be considered together because they determine how much of the scene lands on the chip. Field of view is really about capture geometry, not just a number in a spec sheet. A wide view covers more area, but distant objects get fewer useful pixels. A narrow view concentrates detail on the target, although it makes placement and alignment more demanding, and sensor size changes how that projected image maps onto the active chip area. A fixed monitor may need the right view more than the highest resolution, while a mobile device may need optics that tolerate motion and changing distance. The right choice comes from the scene requirements, not from the biggest marketing number. A small riverbank monitor is a good way to think about these design choices in practice. The same basic camera idea can work very differently once daylight, night operation, and low power all enter the picture. A daytime camera may be enough for simple wildlife detection, but night monitoring often needs infrared illumination to keep the scene visible. If the task grows into tracking movement patterns or estimating depth near the waterline, the sensing hardware may need to become more specialized. That pattern shows up all the time in edge deployments. A prototype can start with a camera, but the production question is whether that sensor really fits the task, the power budget, and the network path. The important sensor decisions all trade one resource against another. Color, light sensitivity, detail, and speed each help in one direction while adding cost somewhere else. That balance is the core design problem. A sensor is not chosen in isolation. It has to fit the rest of the embedded system. Grayscale is cheaper to move and process, so it often works well when color does not matter. RGB preserves more information for detection or classification, but that extra channel data increases both bandwidth and compute. Visible light sensors are the standard choice for ordinary scenes, while infrared-sensitive sensors extend operation into darker conditions or pair well with active infrared lighting. The key issue is not just what looks natural to us, but what wavelengths the hardware can actually measure. Larger pixels often help when light is scarce because each site can collect more photons. Smaller pixels can fit more detail into the same sensor area, so the best choice depends on exposure, optics, and the environment. Higher resolution helps when you need small object detection, text reading, or zoom-free monitoring. The cost is that every added pixel has to move through memory and then through the model, so the system pays for that detail twice. A faster frame rate gives the system a more current view of motion-heavy scenes. It also multiplies the stream of data the processor has to absorb in real time, which can become the limiting factor. A camera choice reaches far beyond the sensor itself. A bigger stream can demand more memory, a stronger processor, or a better uplink. So a modest sensor can sometimes be the better engineering choice if it fits the full operating envelope. When ambient light is not enough, the system can bring its own light source. That changes a dark scene from barely usable to measurable, but also adds power and design complexity. Instead of waiting for the environment to provide enough light, the device actively illuminates the scene and uses the reflected light for imaging. Infrared is especially useful when the goal is night operation with less visible disturbance. That approach is not free. It depends on distance, surface reflectivity, and the sensor's infrared response. Even so, many embedded systems prefer that cost over trying to recover useful information from a dark scene with a passive camera alone. Not every scene needs full frames at fixed intervals. When change is the important signal, a different sensor style can reduce wasted data and better match the task. A standard camera keeps sending nearly identical frames even when nothing changes, but an event camera only reports pixel changes as they happen. That makes it much more efficient in scenes that are mostly static and only occasionally active. The lower data rate eases power and bandwidth pressure, and the signal can be a better fit for fast tracking or machinery monitoring. The trade-off is that the rest of the system has to understand a specialized event stream instead of ordinary video. A side-by-side figure is the cleanest way to compare those sensing styles, because the differences are easier to see than to describe in words. The important idea is that each modality carries a different kind of information and asks the pipeline to do different work. Sometimes a flat image is not enough, especially when distance or geometry matters. Depth-capable sensors add another layer of information, and that changes what the device can reason about. Range imaging can estimate distance. Time-of-flight sensors measure how long light takes to return, and LiDAR builds detailed 3D structure by scanning the environment. Those outputs often become point clouds or related depth representations that are very useful for mapping and obstacle avoidance. Radar becomes attractive when ordinary cameras struggle with visibility or environmental conditions. The cost is extra complexity, calibration, compute, and often more power and space, so the system has to justify that overhead. A navigation or autonomy system is the clearest case for that extra burden because it needs reliable distance estimates and obstacle detection in 3 dimensions. For basic short-range classification, the added complexity may not return enough value. The choice comes down to information need. Add complexity only when the simpler sensor can no longer supply the scene information the task requires. A standard camera is often enough for daylight monitoring and recognition. Infrared helps when darkness would make the device blind. Event sensing helps when change matters more than repeated frames. And depth sensors become worth it when geometry or robustness is central to the task. That ordering matters because the input determines the rest of the stack. Engineers have to balance performance against power budgets and data movement, and the same reasoning shows up across robotics, inspection, buildings, and consumer devices. A sensor is never just about image quality. It is a choice about whether the device can afford to see the world in that particular way. Motion and position sensing sit at the center of edge systems because the device often has to react to the physical world, not just classify data. The goal here is to understand the range of sensors and the trade-off between local awareness and external location. At the edge, the useful signal is often movement, orientation, or location rather than an image or sentence. That matters whenever a system must respond to a change in the physical state around it. A machine that starts vibrating, a wearable that detects a step, or a robot that tracks will travel all need awareness of change. In those cases, motion and position data are the signal the system actually cares about. A field device can stay quiet most of the time and wake up only when its local motion pattern changes enough to matter. That saves bandwidth and power, which is the edge advantage in its simplest form. The sensor choices range from very simple threshold devices all the way to systems that depend on external anchors or satellites. The important part is matching the sensing method to the question the device has to answer. A tilt switch is crude, but it is cheap, durable, and easy to power. When the only need is to know whether something has tipped over, that simplicity is often the right choice. An accelerometer is the workhorse for vibration, impact, movement, and step detection. It works well on the device's own frame of reference, but the readings are noisy and long-term drift becomes a problem once you try to reconstruct motion over time. A gyroscope tells you how fast the device is turning, which makes it valuable for orientation and stabilization. It gives excellent relative rotational motion, but it does not tell you absolute position in space. An IMU combines multiple inertial sensors, so the system can estimate motion, rotation, and changing orientation together. That richer picture is useful, but it comes with calibration, sensor fusion, and drift management challenges. An encoder is attached to the mechanism itself, so it is one of the most direct ways to track movement of a wheel, arm, or shaft. It is precise for relative motion, but it only describes the mechanism's own geometry, not the larger world around it. Time of flight sensing adds spatial awareness by measuring how long a signal takes to come back. That helps with nearby objects and obstacle distance, but it is about range, not motion through time. Real-time locating systems extend awareness across a facility by relying on anchors, beacons, or other installed references. The trade-off is deployment complexity, more hardware, more calibration, and more maintenance. GPS is the standard tool for outdoor asset location because it can report position without a local anchor network. It still depends on signal reception and sky view, so buildings, cover, and power limits can reduce performance. The cleanest distinction is between sensors that reference the device itself and systems that reference the wider environment. That split helps explain why some sensors are easy to deploy while others are more precise but more demanding. Internal reference sensors describe movement relative to the device or mechanism. RTLS and GPS aim for broader location, while time of flight sits in between by estimating distance without placing the device on a map. Relative sensing is usually cheaper and easier to deploy, but it gives only partial truth. Absolute or site-level positioning can be more useful, yet it tends to cost more in hardware, energy, installation effort, and dependence on outside infrastructure. The real design question is how much sensing the application truly needs. Once that is clear, the hardware choice becomes much easier to justify. These sensors produce ordered readings over time, so the system has to deal with sampling, buffering, filtering, and sometimes sensor fusion. A small MCU may be enough for a threshold detector, while more demanding systems need a stronger processor to combine streams or run continuous inference. If the job is only to detect a local change, start with the simplest sensor that can do it. Only move toward richer position awareness when the application genuinely needs direction, rotation, distance, or location. In robotics, wearables, logistics, and industrial monitoring, the hard part is often picking the sensor that gives the model meaningful input. A good model cannot compensate for the wrong kind of signal. Motion and position sensing covers simple local detectors, inertial sensors, encoders, and infrastructure-based location systems. The pattern is consistent. The more absolute the awareness, the more hardware, power, and operational burden usually come with it. Motion and position sensing decides what an edge device can understand about the physical world, from simple disturbance detection to precise tracking and stabilization. The important question is not which sensor sounds most advanced, but which kind of motion information the application actually needs. At the edge, sensing has to earn its power budget. That means the device needs just enough information to classify activity, detect tampering, stabilize a platform, or track an asset without paying for unnecessary computation or hardware. Those questions separate local motion awareness from absolute positioning. A device may only need to know whether it is moving, tilted, or stationary, or it may need a location tied to the outside world. That choice shapes the entire sensing design. A Riverwatch node does not need a full location stack just to notice that it has been knocked loose. If disturbance is the real concern, a motion sensor or tilt sensor can be enough, and the system stays simpler, lower power, and easier to deploy. Different sensor families solve different physical questions. Once the question is clear, the right sensor choice becomes much easier to justify. That framing helps prevent overbuilding. A sensor is not just collecting data. It is answering a specific question about the device or its environment. Some systems only need a threshold decision. Binary orientation sensors answer with a simple yes or no, which is often enough when the real need is to detect a state change rather than measure a precise angle. Tilt switches are crude, but that is exactly why they are practical in many edge devices. They are cheap, low power, and easy to interpret, so they fit tamper detection, safety interlocks, and basic deployment checks very well. Accelerometers measure changes in linear motion. That makes them useful when the device needs to recognize activity, vibration, impact, or gesture patterns rather than exact location. A wearable can learn whether someone is walking, running, sitting, or falling from acceleration patterns. On machines, the same kind of signal can reveal imbalance or wear, and because the data arrives as a time series, it works well with streaming models. An accelerometer tells you how motion changes over time, not where the device is in the world. Mounting quality and calibration matter a lot, because the same sensor can behave very differently when it is loose versus rigidly fixed. Gyroscopes answer a different question: how fast the device is turning. That makes them important whenever orientation changes matter, and linear acceleration alone cannot separate turning from movement. In stabilization and robotics, that turning rate is often the crucial signal. A gyroscope gives a clean view of rotation in the moment, which is different from estimating a fixed position. When the task depends on physical position, a direct measurement is better than inference. Encoders are the sensor family built for that job. Encoders can count wheel motion on a robot or report joint angle on an articulated arm with much finer precision than a general motion sensor. That precision matters whenever a small error can turn into a misplaced object or a missed control boundary. A direct measurement is often more dependable than a model layered on top of noisy signals. Even so, alignment, coupling, and will all affect how trustworthy the reading will be in the field. Distance can also be inferred by timing how long emitted energy takes to return. That approach is useful when the device needs proximity or obstacle awareness without carrying the cost of a full camera system. Time of flight sensing works well for short-range spatial awareness. It becomes attractive when lighting conditions are poor or when a camera would be too expensive, too power-hungry, or too much information for the task. A camera with infrared can extend vision into low light, yet a time-of-flight sensor is often the cleaner choice if only distance matters. The trade-off is a smaller field of view, more surface sensitivity, and a narrower effective range. An IMU combines motion sensors, so a device can estimate how it is moving relative to itself. That compact, always-on view is useful in wearables, drones, robots, and handheld systems. The strength of an IMU is that it fuses signals into a practical picture of current movement. It is small, fast, and useful whenever the system needs motion awareness between larger reference points. IMUs drift because tiny errors accumulate over time. That makes them excellent for short-term motion tracking, but not enough on their own when the device must know its absolute location for long periods. When a question is world location, GPS is the standard reference. It gives a device an absolute position outdoors, as long as it can see the sky and the system can afford the power and integration cost. Fleet tracking, geofencing, and outdoor logistics all depend on that global reference. GPS fits those jobs because it answers location in a map-like frame rather than just local movement. The downside is that absolute positioning usually costs more in power, hardware, and integration. Indoors or near obstructions, reception can also become unreliable, so a field node should use GPS only when location itself matters. Sometimes the target is not the globe, but a site, building, or facility. RTLS answers that local location question by combining tags and infrastructure across the space. Warehouses, hospitals, and factories use RTLS to follow equipment and people through a controlled environment. It depends on anchors, radios, or similar site-level components. So the location system is shared infrastructure rather than a single sensor. RTLS is often the practical answer indoors because it gives context like aisle, zone, or dock instead of raw latitude and longitude. The price is deployment effort, since the site has to be designed around the tracking system. Edge design usually fails when the sensor choice is driven by capability alone. The better habit is to match sensing depth to the actual job and stop there. The most advanced option is not automatically the right one. What matters is whether the application needs activity recognition, exact angle, site location, or only a simple disturbance signal. Each case asks for a different amount of information. More capability usually means more power draw, more calibration, more installation effort, or more dependence on external infrastructure. Sampling rate has to keep up with the motion, range has to cover the physical problem, and calibration has to stay stable enough to trust. Line of sight and installation complexity can decide the outcome just as much as sensor accuracy on paper. Sensor choice also decides the form of the data that reaches the model. That means the hardware decision already shapes the software pipeline before any learning or inference begins. Some sensors produce simple states, while others produce continuous streams or spatial coordinates. Those formats determine whether the next step is a threshold rule, a classifier, sensor fusion, or a localization pipeline. So the sensor effectively defines the shape of the problem. Force and tactile sensing captures physical contact and load directly at the edge. That matters because the signal is local, immediate, and often easy to react to without sending data elsewhere first. The useful idea here is that the device is sensing the world through direct physical effects, not through images or audio. Those signals are often low power and time-based, which makes them a strong fit for fast local decisions. That simplicity is a real advantage. When the sensor produces a stable measurement stream, the system can detect change, watch for faults, and classify behavior with much less complexity than richer sensing modalities. The main sensor families each answer a different physical question. Some only tell you that contact happened, while others measure how much force, shape change, flow, or pressure is present. Buttons and limit switches are the simplest examples. They are dependable when you only need a yes or no answer, but they do not tell you anything about strength, duration, or pattern. Touch sensing extends contact detection to human interaction on surfaces. Capacitive and conductive designs are common in interfaces because they let a device respond locally and immediately, although the hardware has to be designed carefully to handle interference and environmental changes. These sensors are about shape change under load. They're useful when the structure itself matters, but the readings can drift with temperature, mounting quality, and aging, so calibration is part of the job. A load cell is the right tool when the system needs a more exact force measurement. It works well for scales, clamps, and fill level checks, as long as the mechanical load path is well controlled. Flow sensing becomes useful when movement through a pipe or channel matters. A node can flag blockage, leakage, or abnormal use by comparing the live flow pattern with what should normally happen, especially when paired with pressure or contact sensing. Pressure gives you a broader view of what a system is doing internally or in the environment. The reading is useful for safety and health checks, but temperature, altitude, and geometry can all shift the value, so context matters. These signals fit edge systems because they are compact, low energy, and naturally sequential. That makes it easy to turn them into alarms, logs, or small local models that react right away. A switch can trigger a rule, a load cell can feed a classifier, and a flow sensor can expose blockage patterns over time. The key advantage is that the device can make a decision close to the source instead of waiting for a remote system. That sequence is what makes the data so practical for edge analytics. The system can watch for change, trend, and anomaly rather than needing a complete global picture before it acts. These sensors show up wherever physical interaction is part of the job. The use case changes, but the need is the same. Detect contact, force, motion, or pressure reliably at the point where it happens. Robots need touch feedback. Factories need machine health checks. Wearables need compact sensing, and control surfaces need instant response. Each domain depends on a sensor that can survive the environment and still give a usable signal. The real engineering choice is a trade-off. A switch may be enough for contact. A capacitive surface may improve the user experience. A strain gauge may capture structural change, and a load or pressure sensor may be necessary when a measurement has to be precise. That mapping makes the category easy to navigate. First, identify the physical effect, then pick the sensor family that measures it, and finally decide whether the data should be threshold, logged, or classified at the edge. Force and tactile sensing connect edge AI to the physical world. The main question here is how small devices can detect touch, load, deformation, flow, and pressure, then turn those changes into useful local decisions. These sensors do not capture a rich scene the way a camera does. They produce compact signals that are easier to sample, store, and analyze on a device, which makes them a good fit for time series processing at the edge. The sensor family covers a range of physical effects, from a simple press all the way to bending, weight, and fluid behavior. The important part is matching the sensor to the kind of physical change you want to detect. Binary contact sensors are useful because they answer a very direct question. Did contact happen or not? That makes them ideal for tamper detection, collision stops, and other situations where the system needs an immediate yes or no response. Capacitive touch gives a smoother interface because the sensor reacts to a nearby finger rather than a physical click. That opens the door to panels and embedded controls that are durable, responsive, and able to detect richer touch patterns than a simple switch. Deformation sensing tells you not just that something moved, but how its shape changed under force. That is valuable for wearables, tool monitoring, and structural checks, because the model can separate normal bending from sign of stress or overload. Load cells turn force into a stable measurement that systems can trust for weighing, monitoring, and control. At the edge, that often means a local threshold or a small classifier that can tell expected loading from an abnormal condition. The same idea extends to pipes, ducts, tires, tanks, and other fluid systems. These signals are continuous, but they're still compact enough for local monitoring, where the urgent question is whether the system is behaving normally right now. The key distinction is between a signal that simply says yes or no and one that changes by degree over time. That difference shapes how the sensor is processed, how much calibration it needs, and what kind of decision the edge device can make. A button or switch can be handled as an event, while a strain gauge or pressure sensor produces a changing value that has to be interpreted over time. In practice, that means one class of sensors is about state and the other is about measurement. Binary inputs are simple to read, but continuous inputs are more informative and more demanding. They often need filtering, drift compensation, and careful calibration so the system can tell a real fault from temporary fluctuation. That is why these signals are so often handled as sequences. A short run of values can reveal a leak, a bump, a stuck valve, or repeated contact, which makes the data compact enough to classify locally without sending a heavy sensory stream upstream. The edge advantage comes from three practical properties: low power, small data, and fast reaction. Those three together make tactile sensing especially attractive when a device has to work continuously and respond immediately. These sensors are often cheap to sample and cheap to move through a system, so they fit battery devices and always-on monitoring. More importantly, they support local action, which means the device can react at the point of contact or stress instead of waiting for a remote decision. That makes tactile sensing ideal when the job is to detect an interaction or a fault, not to reconstruct a complex scene. The device only needs to know whether touch happened, load changed, pressure drifted, or a part struck something it should not have hit. Two patterns show up again and again. Remote event reporting from small field node and immediate local response from an interface or bumper. Both depend on simple sensors, but they use them in very different ways. A field device like this watches for unusual pressure, flow, or contact and sends data only when something matters. That saves power and bandwidth. And it also keeps the system useful when connectivity is weak or intermittent. For a bumper or a touch surface, the response has to happen right away. The edge logic can stop motion, change state, or wake up a larger model. But the first decision stays close to the sensor because speed matters more than remote analysis. Sensor choice becomes a deployment decision, not just a hardware choice. Matching the modality to the job keeps the system efficient, reliable, and easier to support in the field. Engineers working on real systems need to know when a binary switch is enough, when capacitive touch is better, and when a load cell is required. That judgment determines whether the device fits the job or ends up fighting the job. A poor sensor choice can make a system fragile, power-hungry, or too hard to calibrate. The right one turns a physical problem into a small local decision, which is exactly where edge sensing earns its value. The practical idea is to think first about the physical signal, then about the smallest useful decision the edge device should make. That keeps the sensor choice tied to control, safety, and monitoring instead of raw data collection. When a system needs to sense touch, force, deformation, flow, or pressure, these sensors are often the most direct and economical option. They are especially useful when the goal is to detect contact, spot abnormal stress, or trigger an immediate local response. These sensors all turn physical energy into data the edge device can use. The important idea is not the label of the sensor, but the conversion from a real-world signal into a measurable stream. The first job is sampling the world in a way a model can handle. Once that boundary is clear, it becomes easier to see what the device can detect, how fast it can react, and what kind of processing has to happen locally. Edge AI starts at the sensing boundary before any model runs. A photodiode, magnetometer, current sensor, or radiation detector each captures a different kind of physical change, and that choice controls both the information you get and the speed with which you can use it. A single reading can be misleading, but a sequence tells a story. Drift, spikes, cycles, and early failure signs usually appear in the trend, which is why these sensors are so valuable for local monitoring and detection. The category is broad, but it breaks into a few practical groups. Keeping those groups separate makes it much easier to choose the right sensor for a real system. A simple five-part view works well here. Each group measures a different kind of physical behavior, even though they all feed digital samples into the same edge pipeline. Light-based sensing covers everything from basic brightness detection to more selective color and spectral analysis. The main difference between the devices is how much detail they extract from the incoming light. A photosensor is the simplest version of this idea. It can support occupancy cues, wake-up logic, or display control because it tells the system when light changes enough to matter. Once the sensor separates color bands, the device can start making decisions about material or object type. When a wavelength measurement becomes finer, the same physical principle can support more specialized inspection and composition checks. Optical sensing is very sensitive to the environment around it. A setup that looks clean and stable in one place may become noisy or unreliable when the light changes, surfaces reflect differently, or dust gets in the way. Magnetic and electromagnetic sensors cover a different class of signals, where the system is watching fields rather than light. These are useful whenever orientation, interference, proximity, or emissions carry useful information. A magnetometer gives a direct view of the magnetic field environment. That makes it useful for heading stability, navigation, and also for spotting disturbances that hint at movement or tampering. An inductive proximity sensor answers a narrower question. Is a metal target close enough to affect the field? That makes it a strong choice for presence detection on production lines, where robustness matters more than measuring the field itself. An EMF meter sits at the environmental level and looks for emitted fields or unusual strength patterns. In practice, that can help locate interference, energized equipment, or operating states that change the field around a machine. Electrical sensors move from fields to the power itself. They are often the most direct way to understand whether a system is loading, failing, or behaving outside its normal range. Current and voltage readings are especially useful because they give you a live view of how a device is being powered. A motor feed can show surges or wear, and a voltage line can reveal sag or instability before a fault becomes obvious. The goal is usually not abstract electrical analysis. The goal is a fast local decision: alert, shut down, or create a maintenance ticket when the pattern changes enough to matter. Radiation sensors belong in the same family because they also convert a physical interaction into an electrical signal. The output is usually sparse and event-based, so trend and threshold logic become more useful than one isolated reading. A semiconductor detector turns radiation events into countable electrical pulses. That makes local monitoring practical, especially when the system needs to watch for rising counts, unusual patterns, or a shift in the environment. A useful split is between sensing what is already there and creating a setup that makes the event easier to detect. That distinction changes how reliable the signal is and how much calibration the system needs. Ambient sensing reads the background that is already present in the environment. It is simple to deploy, but the trade-off is that the signal can be weaker or noisier because the sensor has no control over the source. Active arrangements create a clearer event. A beam break at a doorway, a known current path in a machine, or a targeted EMF measurement all turn a physical action into a cleaner edge signal. Active sensing usually gives better reliability, but it asks for alignment and power. Ambient sensing is easier to place, yet it depends more heavily on the environment staying favorable. Most of these sensors become meaningful when they're tracked over time. The shape of the signal often matters more than any single sample. A photosensor can show daylight fading, a magnetometer can show repeating disturbance, and a current sensor can show a fault pattern forming. Those are all temporal patterns, so the stream itself becomes the useful object. That is why classification and anomaly detection fit so well here. The model does not need a full physical theory. It only needs to learn the difference between normal and unusual behavior well enough to act quickly on the device. Choosing a sensor is really about matching the sensing method to the environment. If the conditions are wrong, even a good principle will produce bad data. The best sensor is not the most elegant one on paper. It is the one that still behaves well in the real setting where the device has to work. Sampling speed decides whether fast events are captured, stability decides whether the readings can be trusted, and calibration decides how much setup is needed. Distance, shielding, vibration, temperature, stray light, electromagnetic noise, and background radiation can all push a sensor from dependable to fragile. That is why sensing knowledge matters so much in embedded AI and industrial systems. The model can only work after the problem has been made observable in the first place. A quick comparison helps tie the ideas together. The same hardware family can support very different decisions depending on whether it watches the environment or creates the signal it wants to measure. A Riverwatch node can use a photosensor to follow changing doorway light, or it can use a beam across the corridor to detect passage more directly. One listens to the environment. The other builds a deliberate event, so motion becomes easier to detect. A factory cabinet gives another contrast. Current sensing shows load, while EMF sensing shows field behavior around equipment, and both can feed local anomaly detection from different physical evidence. The choice of sensing modality shapes the rest of the system from the start. It affects power budget, sampling needs, calibration burden, and the kind of compute platform that can process the stream without wasting energy or missing the event. These sensing modalities matter because they turn physical change into something a local system can measure and act on. The focus is on how each signal family supports edge decisions and where the practical limits begin. The key question is not just what the sensor measures, but what that measurement becomes after digitization. Once a signal is measurable in the right form, the system can detect events, classify states, or trigger control. A model cannot make a useful decision unless the world leaves a trace the hardware can actually capture. Light, magnetic field, electrical behavior, or radiation all work only when they vary in a way that tracks the event of interest. That streamlike behavior is what makes them valuable at the edge. A system can watch for pattern boundaries in a time series, even when it never forms a full image or a rich scene understanding. Each sensing family solves a different measurement problem, and that choice determines what kind of edge task becomes practical. The same hardware class can support simple thresholds or richer classification, depending on how the signal behaves. Light sensing is often the easiest entry point because brightness changes are easy to observe and cheap to process. With the right setup, the same sensor can do passive environmental monitoring or a deliberate beam break trigger. Magnetic sensing is useful when cameras or microphones are a poor fit, especially in small or harsh installations. It can detect state changes like a door opening or nearby metal moving into range. Electrical measurements often reveal trouble before anything visible breaks. A drifting current trace or a sagging rail can expose load problems, motor faults, or unstable power long before a larger failure appears. Emission sensing looks at what a device gives off rather than what it directly consumes. That makes it useful for finding switching activity, interference, and abnormal behavior in nearby electronics. Radiation sensing is often about timely local awareness rather than deep interpretation. Thresholds and count changes are enough when the main job is to raise an alert quickly and safely. A major design choice is whether the system watches a natural signal or creates its own measurement condition. That choice affects reliability, power use, and how easy the data is to interpret. Passive setups listen to what is already there, like ambient light or background electrical noise. Active setups add an emitter or other stimulus so the detector can measure a change with more control. That trade-off shows up in real deployments all the time. Passive systems can be lower power, but active systems often win when the event has to be detected cleanly, such as a person breaking a beam in a hallway. Simple detection is often the first job. Did the door open? Did the current spike? Did the reading cross a limit? Once the signal is being captured well, the same stream can support a more detailed model of machine state or behavior. These sensors are often the first line of awareness, not the final judgment. They trigger cameras, control loops, alarms, or heavier diagnostics only when something worth attention has already been detected. A light sensor can wake a camera, a magnetometer can confirm a state change, and a current sensor can flag an electrical anomaly. The point is to spend compute only after a cheap local signal has earned that attention. This is where practical engineering shows up. The right modality makes the problem measurable in the right form, which often matters more than the model itself when a system has to be reliable in the field. Physical signals come with physical constraints, so the sensing design has to account for drift, placement, and interference from the start. Those details decide whether the measurement stays trustworthy over time. The environment changes the measurement, sometimes in subtle ways and sometimes dramatically. A sensor that looks stable in a lab can behave very differently once it is mounted in a real installation. Long-term sensing depends on recalibration and realistic assumptions. Light sensors age and get dirty. Magnetometers pick up nearby metal, and electrical sensors can shift with installation errors or line noise. Placement is not a mechanical afterthought. It changes the meaning of the data. A beam break sensor, a current probe, or a magnetometer can all be accurate in one position and misleading in another. These sensors often live near motors, power electronics, sunlight, vibration, metal, or people moving through the space. Sometimes that disturbance is useful evidence, and sometimes it has to be removed before the reading means anything. Some systems need a steady stream of readings, while others only care about threshold crossings. That choice changes power use, storage, compute, networking, and even how the system fails when conditions are poor. Choosing a modality starts with the observable you could trust. Once that signal is reliable, the rest of the system becomes much easier to design around it. Occupancy may only need ambient light, while a doorway trigger may need an emitter detector pair. Machine health may show up first in current or voltage, and access events may be easier to catch with a magnetometer or inductive sensor than with a camera. The sensor family determines the data's shape, the model you can run, the power budget you can afford, and the failure modes you must tolerate. Before the stack moves upward, that design truth stays central. Measurable signals come first, and the intelligence follows from them. Environmental, biological, and chemical sensing gives edge devices a way to measure the state of the world, a body, or a material environment. The important idea is that these sensors turn physical or biological conditions into digital values that software can track and interpret. That family includes many different technologies, and each one works on a different physical principle. The details matter because deployment, calibration, and failure behavior can vary a lot from one sensor to another. The next step is to separate the umbrella idea from the individual sensor types inside it. Once those groups are clear, it becomes easier to understand what each sensor can measure and what limits it has. Temperature and humidity sensors describe the surrounding environment, while particulate and gas sensors watch air quality and specific compounds. Biosignal and chemical sensors extend the same pattern to living systems and target substances, and all of them feed the edge device with a stream of values it can use locally. Temperature and humidity often act as context for other models, and air quality sensors are useful when the goal is to track pollution or trigger alerts. Gas and chemical sensors go further by estimating the presence or concentration of a substance, which is why they show up in safety systems and industrial monitoring. Biosignals are different because they come from living bodies rather than the environment alone. Heart, brain, breathing, and muscle signals can reveal stress, exertion, motion, or physiological change in real time, which makes them valuable in wearables and health devices. The output is usually not a single snapshot. The common pattern is a stream of readings over time, and that time structure is what makes the data useful for edge processing. A temperature probe may report a value every few seconds, while a particulate sensor may update continuously. Biosignal sensors often capture fine-grained patterns, and chemical sensors may change more slowly, but they still produce temporal data that needs to be interpreted over time. That time series shape pushes the system toward filtering, smoothing, thresholding, and anomaly detection. A single reading may not mean much, but a trend, a spike, or a departure from baseline can be enough to trigger action. A river monitoring node makes the trade-off concrete. A small device near a waterway can sample environmental conditions locally and decide on board whether something is worth reporting. A device like this may measure temperature, humidity, particulate matter, or nearby biological cues, depending on the site. Instead of sending every raw sample, it can classify conditions locally and transmit only threshold crossings, suspicious patterns, or sudden shifts that deserve attention. The Clean Lab version hides a lot of real-world trouble. Mud, condensation, dust, vibration, drift, and intermittent power can all change what the sensor reports, and some devices need a warm-up period before their readings settle down. Once the sensor starts changing, model quality depends on it. The model may be trained well, but if the input hardware drifts or behaves differently in the field, the whole system starts to move away from the truth. A drifting sensor can make a good model look wrong, and a changing environment can demand site-specific adjustment. Ignoring warm-up or replacement issues creates misleading readings and turns maintenance into a real system constraint. These devices look simple only if deployment is ignored. A robust design has to assume aging, shifting response, and changing conditions, so maintenance becomes part of the intelligence rather than a separate afterthought. The practical value shows up in jobs that combine hardware and machine learning. Knowing the sensor family helps you decide whether a failure comes from the model, the placement, or the device itself. Teams building IoT devices, wearables, industrial monitors, or embedded AI products need that judgment all the time. It affects product design, field deployment, and support because a bad sensor can look like a bad algorithm if you do not know what to check. Environmental, biological, and chemical sensors are a broad and important class of edge AI inputs. Their usefulness comes from watching change over time, and their real-world success depends on calibration, drift, warm-up behavior, replacement, and environmental sensitivity just as much as the model that sits on top of them. These sensor domains are where edge AI meets the physical world in its messy, changing form. The important idea is that the model is only useful when it can deal with real signals, real drift, and real deployment conditions. These devices form a loose family rather than one uniform category. They can measure weather, body signals, or chemical conditions, but the common challenge is the same. The data comes from the real world, so it is noisy, variable, and never perfectly stable. That time structure is what makes edge AI valuable here. Patterns over time reveal trends, abrupt changes, and combinations of readings that one sample alone would miss. So context matters as much as the individual measurement. Environmental sensing covers the most familiar physical measurements, from air quality to temperature and vibration. The main question is how local conditions and nearby activity change the reading, because the surrounding environment can change the meaning of the signal. A pollution monitor might combine particle counts with weather variables to separate smoke from dust or sensor noise. In industrial settings, the same kind of local sensing can warn about leaks, overheating, or other unsafe conditions before people notice them directly. These sensors are attractive because they are small, low power, and easy to deploy close to the thing being monitored. But installation details matter a lot. Sunlight, airflow, and nearby structures can bias the data, so the model inherits every assumption made during placement. Biological sensing deals with signals from the body or other living systems, and those signals are often continuous and time-sensitive. Reliability becomes harder here because physiology changes with motion, contact quality, and the person wearing the device. Wearables and medical devices often use pulse, ECG, or EEG-style measurements to spot irregular rhythms, detect a fall, or compare current readings with a user's normal baseline. These are ideal edge AI inputs because the value comes from interpreting a stream, not a single snapshot. The harder part is that the signal processing pipeline has to clean up the raw data before classification even starts. A system has to work across different users and different days, not just in a controlled test setup, or the result is not dependable enough for production. Chemical sensing shifts the focus from motion or temperature to composition. These sensors are especially useful when the question is what substance is present, how much of it is there, and whether the reading has changed in a meaningful way. That makes them common in air quality monitoring, leak detection, water monitoring, and industrial safety. A device might watch for a chemical signature that suggests contamination or a process shift, which is exactly the kind of decision Edge AI can make locally. These sensors often need calibration against known references before the numbers mean much. Many also drift or stabilize slowly over time, so a sensor can still function physically while its output becomes less trustworthy. That means the system has to manage maintenance, not just inference. It should know when readings are still settling, when calibration is due, and when replacement is needed, because ignoring those tasks creates false confidence in the data. A stream monitoring node brings all of these issues together in one real deployment. The useful part is not only sensing the river, but deciding locally which changes matter enough to send onward. A low-power node can watch temperature, humidity, particulate matter, and chemical indicators, then forward only events like a turbidity spike or a runoff pattern. The challenge is keeping those readings trustworthy across weeks and seasons, not just during installation. Small physical problems can distort the picture long before the software notices. That is why Edge AI here is partly a sensing problem and partly a maintenance problem. The model cannot recover information that the sensor has already lost. Real edge systems live or die by the quality of the signal coming in. Good engineering means recognizing when the sensor, not the model, is the weak point and planning for that from the start. Engineers need to separate model error from data quality failure and build maintenance into the product itself. Those choices affect reliability, support effort, and the true cost of ownership more than another model tweak often does. Environmental, biological, and chemical sensing connect edge AI to pollution, health, and deployed condition monitoring. but only when calibration, warm-up, drift, and replacement are handled realistically. The model matters, but dependable sensing is what lets the model earn trust in the first place. Edge AI depends on more than raw sensor readings. The important idea here is that a device also uses information about itself and about its network surroundings to make better decisions. That widens the input space beyond the outside world alone. A practical edge system listens to the physical environment, but it also pays attention to internal conditions and external digital signals. A microphone or camera is only part of the story. Power use, latency, reliability, and control all depend on signals that describe the device and its surroundings, so those signals have real operational value. Virtual data covers anything the device can use that does not come straight from physical sensor. That includes battery level, temperature, logs, remote commands, forecasts, and API responses, and all of it can be folded into one decision loop with the sensor stream. The first category is self-observation. These inputs tell the system about its own health and resources, which lets it adapt before a problem turns into failure. Think of device observability as the edge version of looking at your own dashboard. Battery, memory, heat, connectivity, and timing all tell the controller how much room it has to work with. Those signals should change behavior immediately. Low battery can reduce sampling, tight memory can drop low-value buffers, heat can slow inference, a weak radio can trigger batching, and fault logs can push the device into a safe mode. A river monitoring node has to protect its own lifespan while it watches the water. If power is running low, it should save energy for important alerts instead of spending it on routine traffic. This is not just diagnostics after the fact. The device's own state becomes an input to control, so it can keep functioning sensibly when the network is absent or the resource budget is tight. The second category points outward. These signals come from connected systems and remote services, and they let the edge device make better local choices with wider context. An edge device can use information that arrives over the network, such as fleet summaries, weather data, or control messages. That external context can improve the local decision without moving the whole control loop to the cloud. A gateway can compare summaries from many field nodes and focus attention where the signals look unusual. That turns the gateway into a coordinator for the local deployment, not just a passive relay. A heating controller can combine its own sensor reading with a forecast and avoid pushing the room too far past the target. External data makes the local action more informed, while the device still keeps control close to the hardware. Remote instructions matter too, especially for mobile systems. A robot or drone may need to change course, pause, or retask itself when a fleet-level command arrives, while still assuming the network may disappear at any moment. The real design challenge is combining all three streams without giving up autonomy. The device should use whatever context is available, but it still needs to act safely when some inputs vanish. A good edge controller may read local sensors, check its own battery, and consult the weather before acting. If connectivity drops, local rules and history still carry the decision forward instead of stalling the system. That mixing process is data fusion. The important part is resilience. Outside information should make the device smarter when available, not dependent on the cloud when it is not. This is why hardware choice matters so much. The platform has to collect signals, expose its own state, communicate reliably, and still leave room for control logic to run on the device itself. That broader view changes how hardware gets evaluated. The question is no longer only speed. It is whether the board can support the full information loop the application needs. A capable board needs more than compute. It should expose health clearly, keep telemetry available at low power, handle intermittent connectivity, and fall back cleanly when the link disappears. That is the bridge to the rest of the stack. Processor, memory, radio, and control hardware all exist to make those data flows practical under real constraints. The job signal is clear here. Production edge work rewards people who understand device health, logging, and coordination, not just model output. Hiring teams often want engineers who can reason about battery life, fleet observability, and intermittent networks. Those constraints shape how the system behaves in the field long before model accuracy becomes the main issue. The practical rule is to design for both sides of the loop. Good hardware supports sensing, telemetry, communication, and control together, so the device can act well in the real world. Edge AI also depends on signals that do not come from traditional sensors. That broader view matters because it changes how a device decides, adapts, and stays useful in real deployments. A device can base decisions on information generated inside itself, shared by surrounding equipment, sent by a human, or fetched from a network service. Once those inputs are part of the model, the device is reacting to more than the physical world. That wider class of inputs is useful enough to name on its own. Virtual data covers any meaningful signal that an edge system can use without directly sensing the outside world, and that often separates a simple detector from a system that can act intelligently. A clean way to organize these signals is to split them into two groups. One comes from inside the device, and the other comes from outside the device but still feeds its decision loop. That split makes the design problem easier to reason about. It tells you whether the device is learning from its own condition or from the environment around it. Introspective data is about self-awareness. The device watches its own logs, resource use, link state, and internal measurements so it can manage health and behavior instead of running blindly. Logs tell the story of what the unit has been doing. Even when storage is limited, a small set of records can make failures diagnosable without sending the hardware back for inspection. Resource usage matters because edge systems live under hard limits. A model that looks fine in a lab can become unstable when memory gets tight, power drops, or heat builds up. Communication state tells the device how reliable the connection is. If the link is weak or intermittent, the system may need to buffer data, simplify behavior, or keep operating without waiting for the cloud. Internal sensors are still physical measurements, but they describe the platform's own health rather than the outside environment. A temperature or voltage spike can force throttling or a lighter workload to keep the device safe. Extrospective data comes from outside, yet it still changes what the device should do. These signals expand the decision space by bringing in neighbors, commands, remote services, and network context. Connected system inputs let one device benefit from what another device has seen. A gateway can combine readings, compare trends, and make a stronger local judgment than any single node could make alone. Remote commands change priorities from the outside. A robot or drone may receive a new goal, a safety limit, or an immediate stop, and the onboard logic has to fold that command into its own control decisions. API-fed context adds information the device cannot sense directly. A heating system that sees forecast data can act on expected conditions, not just the current room reading, which makes control more efficient. Network data gives the device a view of broader traffic and protocol state. In fleet or industrial settings, that can decide whether the system should act locally, wait for coordination, or hand work off elsewhere. That broader taxonomy matters because edge AI is not only perception. The device may classify an image or score audio, but it also needs enough context to save power, obey a human command, synchronize with peers, and keep running when the cloud is unavailable. Multiple streams matter because real deployments are messy. One signal can mislead, while a small set of signals can turn an uncertain guess into a dependable decision. Fusion is where the value appears. When the device compares several inputs instead of trusting just one, it can separate a real event from noise or a temporary glitch. A waterway node can use its own sensor reading, battery state, link quality, and recent logs together. If power is low and the connection is unstable, it may buffer the event and defer heavier analysis until a gateway is available. A drone shows the same pattern. A remote goal tells it what to aim for, while telemetry tells it whether the hardware can safely keep going. High temperature or poor connectivity can justify a route change or an early return. Agriculture makes the blend easy to see. Soil readings, forecast data, and a farmer's command can all affect scheduling. So the edge node responds to current conditions, expected change, and operator intent together. That combination improves robustness. A device with only network dependence breaks when the link drops, and a device with only local sensing acts blindly when the larger context changes. Fused inputs let it degrade gracefully instead of collapsing. Hardware choice changes once virtual data is part of the input surface. The platform has to expose telemetry, keep logs, watch its own health, handle queues, and keep local control available when outside services disappear. That is why selection often starts with observability, power, and communication before model size enters the discussion. The chip matters, but the surrounding platform determines whether all of these signals can be used reliably. The job market angle becomes clear from that same requirement. IoT, robotics, industrial monitoring, and connected products all need engineers who can work with device state, neighbor coordination, commands, and unreliable networks. The broader design lesson is that edge AI input includes the device itself, nearby systems, external services, and human control channels. That view leads directly to the next layer of the stack, where processor, memory, radio, and control hardware determine how those signals are handled. Edge AI hardware architecture is about how a device is built and how its parts work together under real limits like power, heat, and size. The structure of the system matters as much as the individual chip inside it. The important idea is connection, not just collection. A device only works well when computation, memory, sensors, and communication are linked in a way that moves data efficiently. That definition matters because edge AI is a system problem. Data has to travel from sensors into memory, get processed on the right hardware block, and then leave through radios or buses without wasting time or energy. A block diagram helps organize the thinking. The processor runs control logic, memory holds data, coprocessors speed up repeated work, peripherals connect the outside world, and the links between them decide how smoothly the system can move information. The application processor usually sits at the center of control. It coordinates the device, schedules tasks, and decides when other hardware should wake up or stay quiet. This chip is the home for the main software flow. It handles the logic that makes the device feel organized, instead of like separate parts acting on their own. Inside the processor, some hardware blocks can take over tasks that repeat a lot. An FPU is one example, and DSP or linear algebra support plays the same role in many edge AI chips by handling math more efficiently than software alone. That difference shows up quickly in real devices. If audio filtering or small matrix operations happen often, dedicated hardware saves energy and leaves more room for the rest of the application. Memory has two jobs, and they are very different. One kind is for fast working space, and the other is for keeping software and data when power is off. RAM holds active code, temporary results, and sensor buffers, but it disappears when power is removed. Flash and RAM keep firmware, settings, calibration data, and often the model itself. That split shapes board design every day. A small device may only need enough RAM to run its control loop, while Flash holds the program and external buffering absorbs data bursts that arrive too quickly to inspect immediately. The real question is whether the system can hold the incoming data pattern long enough to process it. A device can boot correctly and still fail if it cannot buffer the live stream for the physical world. Proximity is a design decision with real consequences. Whether a component sits on the same silicon or on a separate chip changes speed, energy use, and how much flexibility the system has. On-die parts are physically closer to the core, so the data path is shorter and usually cheaper in energy. Off-die parts live farther away, which adds communication cost, but often gives more room for capacity or expansion. An integrated design is attractive when low power and responsiveness matter most. A separate component can be easier to scale or replace, but it usually pays for that flexibility with slower access and extra energy spent moving data. That trade-off often changes from prototype to product. Development boards tend to be roomy and modular, while production hardware usually moves toward tighter integration to save power, space, and parts count. Some acceleration lives outside the main chip altogether. A discrete coprocessor adds real capability, but also becomes part of the system's power, size, and thermal budget. Like integrated acceleration, these chips are specialized for certain workloads. The difference is that they sit off die and usually connect through the package or board instead of sharing the same silicon with the processor core. That pairing can move a system from handling only very small local inputs to handling much richer visual or numerical streams. The trade-off is that the device also moves into a different thermal and power regime, so the whole design has to be reconsidered. These terms are practical vocabulary. They force the discussion toward bandwidth, energy, package size, and whether the workload truly fits the board instead of just sounding advanced on paper. Peripherals are the device's bridge to the outside world. They are what lets sensors, storage, radios, and wired links talk to the compute core. Without these pathways, the processor is isolated inside its package. The rest of the system becomes useful only when data can move in and out through the right interfaces. That matters a lot for Edge AI because the model is only one part of the pipeline. A camera, microphone array, sensor bus, or network interface can change the whole behavior of the device depending on how data arrives and how it leaves. Once the hardware roles are clear, the right questions become easy to ask. The goal is to match the board to the workload, not just to the model name on a spec sheet. That viewpoint is the foundation for the rest of the chapter. Once a device is seen as a connected system, it becomes much easier to choose hardware that fits time series, audio, images, video, and other edge workloads. Edge hardware becomes much easier to reason about when the architecture is read as work moving through a system. The goal here is to connect the diagram to real design choices, where sensing enters, where computation happens, and what leaves the device. A hardware diagram is most useful when each block is treated as a job rather than a label. That view helps turn a static picture into a practical way to trace data, compute, storage, and communication. The simplest way to read the stack is to follow the path of the data. Sensors bring information in, the processor decides what to do with it. RAM holds what is active, persistent storage keeps what must survive power loss, and networking or peripherals send out only the result that matters. That means a device is rarely just one chip doing one job. The application processor usually coordinates the whole system, while the surrounding blocks handle specific tasks, so the main core does not waste time or energy. Visual evidence matters because it exposes boundaries that are easy to miss in text alone. A sensor on a bus tells you data is being formatted and filtered locally. A radio or Ethernet block shows where the network boundary is, and a coprocessor tells you some work is being handed off instead of forced through the main core. Once the data path is clear, the next useful question is where the processor keeps active work and where it keeps durable information. That distinction is central to how an edge device starts, runs, and updates. RAM is the fast workspace for live sensor windows, intermediate features, and anything needed right now. Flash or ROM holds code, models, calibration, and configuration across power loss, so it shapes startup behavior and update strategy. A river monitoring node makes the trade-off concrete. It can wake on sensor input, inspect a short window in RAM, keep its model in Flash, and send only a small alert when something meaningful happens instead of streaming raw data all the time. The same logic appears in audio and vision devices. They buffer only the active data locally, keep detection logic in non-volatile memory, and transmit a trigger or compact result when local filtering is enough. The next question is where extra compute lies. Some acceleration is built into the processor itself, while other acceleration sits on a separate chip, and that changes both performance and system design. Integrated coprocessors speed up specific workloads without adding another full chip to the board. That can include DSP blocks, vector units, or NPU-like engines that make repeated signal processing much more efficient. For audio framing, filtering, feature extraction, or simple inference, that extra hardware can cut the load on the general-purpose core. In a battery-powered device, that difference often decides whether the system can stay on continuously. A separate accelerator is useful when the workload is larger than the main processor can comfortably handle. It gives the application core room to stay responsive, but it also adds board space, power cost, and coordination overhead. On-die hardware wins when latency and efficiency matter most because the data moves a shorter distance and the handoff is simpler. Off-die hardware is attractive when capacity, replaceability, or future growth matters more than tight integration. Peripherals are the point where the device meets the outside world. They matter because every sensor, radio, and storage link depends on them for timing, fidelity, and communication. These interfaces are how the board actually talks to hardware. They may look small in a diagram, but they often determine whether the system can even receive and send data correctly. They decide whether sensor data arrives cleanly, whether timestamps stay aligned, and whether results can be reported without flooding the network. A node that sends only alerts is far easier to support at the edge than one that tries to backhaul raw data all the time. That is why the block diagram is so valuable. It makes it easier to decide what stays local, what can be offloaded, and what should be moved only when a latency, bandwidth, or battery constraints allow it. Once the blocks are readable, the architecture can be discussed the way engineers and product teams actually discuss it. The diagram becomes a tool for choosing where pre-processing belongs, how much to aggregate, and how much hardware complexity the deployment can support. That vocabulary helps in design reviews and interviews because it gets specific about placement and failure modes. You can point to memory, accelerators, and connectivity and explain exactly what the device can still do when the network is weak or unavailable. The same reading skill supports cost decisions, battery planning, model sizing, and system coordination. Different roles care about different constraints, but the hardware map gives each of them a common way to reason about the device. By now, the diagram should feel like a map of work rather than parts list. Sensing enters, computation happens, data is buffered, results are stored or transmitted, and only the right information leaves the device. Microcontrollers and DSPs are the core compute blocks that make edge AI practical on small hardware. The important question is not just whether a device can compute, but which kind of compute fits the sensor, the timing, and the power budget. This layer sits closest to the sensor and handles the smallest, cheapest decisions. From there, the rest of the system can stay asleep until a stronger response is actually needed. A microcontroller is the chip that wakes up, samples a signal, makes a simple decision, and goes back to sleep. That makes it ideal for embedded control, where firmware runs directly on the chip and the device has to be reliable, cheap, and power efficient. Different edge tasks put pressure on different limits. A slow periodic sensor, an always-on keyword detector, and a vibration classifier all need different amounts of memory, latency, and energy, so the right hardware is the one that can stay within those limits for the whole duty cycle. The next question is what an MCU is actually good at. Its design is centered on embedded memory, simple control flow, and fast startup, which is why it works so well for small always-on systems. An MCU combines the processor, memory, and input-output on one chip, so the whole device stays self-contained. Flash usually holds the firmware, RAM holds live state and buffers, and that split keeps boot time short and the system easy to deploy. Low-end parts are excellent when the logic is straightforward, like polling a sensor or sending a reading. Their limits show up when the workload needs more memory, more numeric work, or longer streaming calculations than the chip can comfortably hold. A small monitoring node can use that low-overhead controller layer to keep the system alive. The MCU handles the periodic checks and basic rules, while heavier processing can be handed off only when the signal becomes more demanding. Higher-end microcontrollers sit in a useful middle ground. They can run modest embedded machine learning because they offer more memory, better floating point support, and sometimes vector-style instructions that speed up repeated data operations. Signal-heavy workloads push the hardware in a different direction. DSPs matter because they are built around repeated math on sampled data, which is exactly what audio and other streams need. A DSP is tuned for operations that repeat over and over on a stream of samples. Multiply, accumulate, filtering, windowing, and transforms are the kinds of routines that benefit from that architecture, especially when latency has to stay predictable. Wakeware devices are a good example because they cannot afford to wake a large processor for every quiet moment. They need a path that can keep listening frame by frame and decide quickly whether the target word is present without wasting battery. That is why voice assistants often use DSP-style hardware or DSP-like blocks. The challenge is not model size alone. It is keeping a continuous stream of audio moving through the system at low cost long enough to remain always on. Real products usually divide the work instead of forcing one chip to do everything. Heterogeneous compute means each processor takes the kind of job it handles best, which is often the only way to meet power and latency limits at the same time. A small controller can manage sensing and power states, while a stronger MCU or DSP-class block handles feature extraction or short inference bursts. That split keeps the system efficient because the expensive compute only wakes up when the data really needs it. That separation is often what makes a field device workable. The always-on path stays simple and low power, and the heavier path is reserved for moments that justify the extra energy. A practical node may let one block watch the sensors, another extract features, and another decide whether to transmit or escalate. That is true concurrency in embedded systems, separate compute elements doing different jobs at the same time. These trade-offs show up directly in embedded and edge-oriented roles. The skill employers want is the ability to fit intelligence into constrained hardware without breaking the limits on power, memory, or response time. Job titles may vary, but the same question keeps returning. Can a design work on small battery-powered hardware and still behave reliably? That makes hardware awareness a real differentiator, not just a niche detail. A fast processor is not enough on its own. The better habit is to check the signal type, how often the device wakes, how much memory the workload needs, and whether the system must respond continuously or only in bursts. That is the practical Edge AI lesson. The right hardware depends on the data, the timing, the memory footprint, and the energy budget. MCUs, DSPs, and mixed chip designs are the everyday tools for making that match work in real products. Processor choice decides whether Edge AI stays small, timely, and affordable. The rest of this part compares microcontrollers and DSPs by the kind of work they handle best. A sensor only gives raw data. The processor has to turn that data into an action before time, power, or cost run out. That trade-off is what makes hardware selection just as important as the sensing itself. Microcontrollers fit the control side of embedded systems, where one chip has one main job and has to do it predictably. That predictability is what makes them so common in small edge devices. Running firmware directly on the chip removes a lot of scheduling and software overhead. Boot is quick, interrupts are easier to manage, and the path from sensor input to decision stays short and reliable. That narrow role is exactly the point. Wake up, read a sensor, enforce a rule, drive an output, and go back to sleep if needed. When the product has to be cheap, small, and frugal, that kind of focus controller is often the right fit. MCUs are not all the same. The main difference is how much room they give you for code and data. The higher-end parts make local processing much more realistic. A low-end part is great when the job is simple, but memory limits arrive fast. Flash holds the program and model. RAM holds the live working state. And when both are small, even modest processing pipelines start to feel cramped. Those extras do not make the chip a server, but they do make math-heavy work much more practical. Floating-point operations become easier. Vector-style instructions speed up repeated calculations, and small on-device models can do real signal processing instead of just basic thresholding. The same device can stay focused while its capability changes. In one version, it only watches thresholds and forwards alerts. In another, extra memory and compute let it smooth the data, extract features, and classify events before anything leaves the node. DSPs come into play when the workload is mostly repeated math on a stream of samples. Their job is to make signal transformations fast and efficient. That specialization matters for audio and sensor pipelines, where the same operations happen over and over. Keyword spotting is a good example. The system listens continuously, turns audio into features, and looks for a trigger phrase without wasting energy on general-purpose computation. An always-listening device cannot afford to process every sample in an expensive way. A DSP often handles the front end efficiently, while another processor can take over control logic or higher-level inference when the signal is worth deeper analysis. Once the workload has different kinds of tasks, the cleanest design is often to split them across different processors. Each chip can then do the kind of work it is best at. This is not just about having more hardware. One processor can manage sensors and power, another can process data, and a third can take on heavier work at a gateway, if local resources are too limited. Real devices rarely do one thing at a time, so the architecture has to reflect that mix. A camera system, for example, may separate capture, enhancement, inference, and communications, and a sensor node may keep local logic simple while forwarding richer data when needed. Processor choice comes down to fit. The workload, the timing, the battery, and the rest of the system all shape the answer. The right chip is the one that matches those constraints without wasting resources. A tiny MCU can be perfect for simple sensing and control, while a stronger MCU can handle richer local processing. A DSP becomes attractive when continuous feature extraction matters, and a multi-chip design wins when one processor cannot cover every requirement cleanly. These choices show up everywhere in embedded work because real products have to survive outside a lab. The people who can balance hardware limits with AI needs are the ones who can make a design work in practice. Edge work is rarely just model selection. It demands judgment about firmware behavior, memory use, battery life, and how to split tasks across chips so the system stays stable and efficient. That is why the processor class matters so much. It sets the ceiling on performance, but also on whether local AI is practical in the first place. A good model on the wrong chip still fails if the hardware cannot support it. A system on chip, or SoC, combines many computer functions on one chip, so the device can act like a small general-purpose computer rather than a simple controller. The point to watch is how this changes the hardware choice for edge systems. More integration, more software capability, and a very different development model from a microcontroller. An SoC folds the CPU, memory interfaces, graphics, wireless support, and other pieces into a single package. That integration is what pushes it beyond a stripped-down controller and toward a compact computer, with enough room for richer software and more coordinated subsystems. The main shift is the software layer sitting on top of the hardware. Once that layer appears, the developer is no longer talking directly to every device detail all the time. Many SOCs run an operating system, often an embedded Linux variant, and that changes almost everything about how the device is used. The OS manages processes, scheduling, drivers, files, networking, and security. So application code can sit on top of an existing stack instead of handling every hardware interaction itself. That extra abstraction is useful because it speeds development and makes prototypes easier to build. The trade-off is that the system usually draws more power, produces more heat, and has more software pieces that can interact in unexpected ways, so the design is less simple than a bare-metal microcontroller setup. SOCs show up where the edge device needs flexibility, not just low power. The workloads are broader, and the hardware has to support them all at once. Phones, gateways, and industrial systems all need local compute for displays, networking, sensors, logging, security, and application logic. Those jobs go well beyond a tiny sensing node that wakes briefly, reads a value, and goes back to sleep. Most SOCs bring together multi-core processors, larger memory, wireless connectivity, and often graphic support. That gives enough headroom for near real-time audio or video inference when a model and pipeline are designed to fit the device, especially when media and networking are part of the workload. Edge AI products rarely do only one task. A camera system may classify images, compress frames, timestamp events, and talk to the network, while a voice system may need wake word detection, local controls, and secure connectivity. An SoC can hold those pieces together on one platform. A concrete example makes the hardware choice easier to see. As the Riverwatch node grows from a simple sensor node into a richer local intelligence platform, the balance starts to shift toward an SoC. If Riverwatch node only samples a few signals, runs a lightweight classifier, and sleeps, a microcontroller is the natural fit. Once the design adds image classification, audio detection, or heavier networking, an SoC becomes the more practical platform for the prototype. That choice gives the team room to change the design without rebuilding every software layer at once. The operating system, the camera or microphone pipeline, the networking stack, and the application logic can all live together while the product idea is still moving. Embedded Linux is popular because it already solved a lot of the hard software problems around drivers, file systems, and deployment. The important idea, though, is broader than Linux itself. SOCs are chosen when an operating system layer makes the device easier to build and manage. Linux is a common foundation for SoC-based devices because it gives a mature environment for hardware access and application deployment. The deeper point is that the OS becomes the mediator between software and hardware, which is exactly what many edge products need. The final decision comes down to workload shape. When the device is software-heavy, sensor-rich, or likely to grow, the SoC starts to make more sense than a minimal controller. An SoC fits especially well when the job involves audio, imaging, or moderately complex local inference. Its integrated CPU, memory, graphics, and networking make it easier to build a complete product instead of a narrow demo board. That hardware choice matters for jobs too, because embedded AI work often crosses multiple layers. A person working in this area may need to understand the hardware limits, the Linux stack, the application code, and the system integration all at the same time. An SoC is the right fit when the edge device needs broad capability, familiar development tools, and enough compute for richer local intelligence. It gives up some simplicity and efficiency, but it often becomes the difference between a narrow controller and a real edge computing platform. A system on chip matters because it turns edge devices into compact computers, not just simple controllers. The rest of this part focuses on what that extra integration enables and what it costs. That integration changes the whole shape of the device. Instead of scattering functions across many chips, the SoC brings compute, memory access, communication, and I/O together, which makes the system smaller, simpler to wire, and capable of running much richer workloads. That phrase captures the real idea. The value is not only speed, but the platform around the processor. Once the hardware is integrated, the device can behave more like a small computer and less like a tightly limited controller. A microcontroller works well when the job is narrow and predictable. An SoC fits when the product needs to manage data, run libraries, handle interfaces, and keep an inference pipeline moving without running into hardware limits all the time. The operating system is a major part of that difference. With Linux-based development, engineers rely on drivers, services, file systems, networking stacks, and application frameworks, which speeds up reuse but also adds more layers that have to be configured and kept under control. That is the core trait. Direct control gives very tight timing and resource use, while an OS gives portability and faster development. Edge AI often benefit from the second option because one device may need to sense, buffer, classify, log, and stay connected all at once. More capability usually comes with more power draw, more heat, and more design pressure. Those effects show up in battery life, enclosure design, and long-term reliability. So the cost is not just financial. It is also thermal and operational. A stronger SoC can run bigger models and richer software, but it pays for that with higher energy use. That can shorten battery life, force cooling decisions, and make thermal behavior part of the product requirements from the beginning. That is why socks are so useful in early prototypes. They let a team validate sensing, inference, and the full data path quickly. But the same prototype may still be too power-hungry or too expensive for the final deployment. So the platform choice has to be revisited once the workload is understood. The strongest fit appears when the device must handle streams, interfaces, and networking together. Audio, video, and connected products all benefit from the extra memory, compute, and communication support that an SoC brings. Those workloads need more than one kind of resource. Frames and models need memory. User interfaces need graphic support. Background tasks can be split across CPU cores, and networking keeps the device tied into the larger system without extra hardware. A wakeware device or a smart camera is coordinating several jobs at once, not just making a single decision. That is why the SoC becomes the center of a local software stack rather than just a compute block. That flexibility makes SOCs a strong starting point for many teams. The first goal is usually to get a working system quickly, and only after that does it become clear whether the final product should stay on the same platform or move to something leaner. Familiar tools and broad software support help engineers move from idea to testable system quickly. If the final workload demands more efficiency, the platform can be revisited later. If it needs connectivity, peripherals, and enough compute for real-time edge AI, the SoC may remain the right foundation. That is also why SoC experience transfers well across many jobs. The valuable skill is not only writing software, but connecting software to power limits, networking needs, and deployment constraints on a real device. Platform choice depends on the actual job the device has to do. Use an SoC when you need an operating system, richer peripherals, multi-core compute, and support for mixed workloads. Choose a simpler target when efficiency, simplicity, and thermal control matter more. Deep learning accelerators are dedicated hardware for model inference, and the key idea is specialization. They trade general-purpose flexibility for much better speed and efficiency on the math that neural networks repeat. A microcontroller, or SoC, has to handle many jobs, so it stays broad. An accelerator narrows the job to the parts that matter most for inference, especially repeated matrix-style computation, and that focus is what makes it efficient. Neural networks spend most of their time doing dense numeric work, not general logic. When hardware is built around multiply-accumulate loops and similar patterns, it can keep more compute units active, move less data unnecessarily, and get more result for the energy it spends. The practical question is which part of the node should carry the model workload. That choice depends on the model size, the timing requirements, and how much power the device can afford to use. A small model at a modest sampling rate can fit comfortably on a microcontroller. Once the node needs more model capacity and still has to respond quickly within a tight power budget, an NPU or similar accelerator becomes a better fit. The real decision is about structure, not raw speed. If the workload is regular and repeatable, specialization pays off. If the processing is changing all the time, a flexible processor may absorb the system's complexity more cleanly. Accelerators come in several forms, and the differences matter because each design makes a different trade-off between efficiency, programmability, and support for changing workloads. Some are extremely narrow, and some are much more adaptable. Thinking in terms of a spectrum helps explain why two chips can both count as accelerators but serve very different system needs. At the specialized end, fixed function chips spin silicon on the exact operations they expect to see. That gives them excellent latency and power behavior when the workload matches their assumptions. A GPU-like accelerator keeps more flexibility in the design, so it can adapt to a wider range of models and tool chains. That flexibility costs some efficiency, but becomes valuable when the software stack is still changing. Most practical systems land somewhere in the middle. They push the repeated math onto an accelerator, while the host processor keeps control of the surrounding logic and the less regular parts of the workload. That trade-off shows up everywhere in hardware design. A general system pays for adaptability with extra energy, while a specialized one can often do the same inference path with much less overhead. Once the hardware is chosen, the next question is how the work gets divided between the host and the accelerator. That split keeps the system understandable and helps each part do the job it is best at. The host handles orchestration, communication, buffering, and scheduling. The accelerator runs the inference path itself and returns the result, so the expensive math is isolated from the rest of the device logic. That separation makes the system easier to reason about. In a wakeware device or a monitoring node, the host stays in charge of sensors and power states, while the accelerator handles the classifier and the repeatable model work. Accelerators are broader than the usual NPU idea. Some designs move toward different computational models entirely, and that widens the set of problems edge hardware can handle well. Neuromorphic and spiking systems change the style of computation rather than just speeding up conventional tensor math. They can be attractive when the input is sparse or arrives in bursts instead of as a steady, dense stream. If a sensor mostly sees quiet, unchanging data, event-driven hardware can spend its effort only when something important happens. That does not make it universally better, but it does show that inference hardware is not limited to one design pattern. Accelerator selection is a moving target because the hardware, the tools, and the supported models keep changing. What looks best on paper can shift quickly once the software stack improves. A chip's value depends on more than its peak speed. Tooling, operator coverage, quantization support, memory behavior, and model conversion all shape whether the device is actually practical for a given workload. Those terms are clues about throughput, latency, and power budget. Reading them well tells you what part of the workload is being offloaded and where the design may be giving up flexibility to gain efficiency. The big idea is that edge AI often works best when the compute is split. The accelerator handles the regular math, and the host handles everything else. Once that split is clear, the choice between a microcontroller, an NPU, or a more flexible processor becomes much easier to reason about. Deep learning accelerators matter because the shape of the workload determines whether specialized hardware is worth the cost. The focus here is on where they fit, what they do well, and where their limits show up in real products. The first thing to look at is the structure of the computation. If the work is mostly repeated matrix math and accumulation, the hardware can be built around that pattern instead of treating it like a general-purpose problem. Neural networks spend a lot of time doing the same numeric operations over and over, especially multiply-accumulate work. That regularity makes them a good match for silicon that is tuned to move data efficiently and execute one kind of operation at very high throughput. At the edge, the question is rarely maximum raw speed. The real target is getting a prediction fast enough while staying inside a battery, heat, and enclosure budget, so the chip has to fit the product rather than dominate it. Accelerators are not all designed the same way. Some are tightly specialized, while others stay closer to the flexible style of a GPU, and that difference shapes everything from efficiency to long-term adaptability. A fixed-function accelerator can be extremely efficient because the hardware is built around a known set of operations. The cost is flexibility. Once the supported model family changes, the hardware may be much harder to use. A more flexible accelerator can handle a wider range of operators and model types, which helps when the product is still evolving. That broader support usually comes with some loss in efficiency, power, or silicon economy compared with a highly specialized design. The real decision is not just speed, It is how tightly the hardware should be matched to one workload family. Narrow coupling can deliver impressive efficiency, while broader support makes the platform easier to build on and more resilient to model changes. In most edge systems, the accelerator works beside the main processor rather than replacing it. The host still runs the device, and the accelerator takes over the heavy inference step when the workload justifies the extra hardware. Sensor handling, networking, security, logging, and user interaction still belong on the MCU or SoC. The accelerator is a specialist for the math, not the part that coordinates the whole device. Edge products wake, sleep, buffer data, handle interrupts, and make policy decisions all day long. Faster inference helps, but it does not remove the need for a controller that keeps the system organized and responsive. Riverwatch Node shows that split clearly. The host can keep timing and communication lightweight, while an attached accelerator handles a vision or audio pass when the classifier needs more throughput than the main processor can comfortably supply. The strongest fit appears when the workload is continuous and latency sensitive. That is where the same calculation repeats often enough that saving energy on every pass really changes the product. Always-on audio is a good example because the device must listen constantly. Even if the model is small, the repeated inference load makes a compact accelerator valuable for keeping battery use under control. Camera pipelines are another strong match because frame-by-frame processing adds up fast. Once audio, vision, or other streams are combined, the compute burden grows again, and accelerator support can keep the system practical instead of thermally overloaded. A small intermittent model may run well enough on the host itself, so an accelerator would add cost without much benefit. The right question is whether the model, the toolchain, and the power budget all point in the same direction. Model support shapes the whole engineering process. The more constrained the accelerator is, the more the model has to be designed around the hardware instead of the other way around. If only certain operators or quantization schemes are supported, the team has less freedom to experiment or change direction later. Broader support gives more room to adapt, but it usually costs some efficiency. A chip can look good on paper and still be painful if conversion tools are fragile or deployment requires awkward model surgery. In practice, the buyer is choosing a production path, not just a compute number. There is also a more unusual branch of accelerator design that follows a different idea of how computation should happen. Neuromorphic systems are not just another flavor of NPU. They aim to process information in an event-driven way inspired by spikes. These systems try to represent and process information with sparse events rather than dense tensor pipelines. That makes them fundamentally different from the mainstream deep learning accelerators most teams use. When the computation is sparse and event-driven, power use can drop a lot for the right task. The trade-off is a different software stack, different model support, and a much steeper path from familiar deep learning workflows to deployment. These systems make the most sense when the problem itself already behaves like a stream of events. That changes the architecture conversation quite a bit, so they're usually a design space option rather than a direct replacement for mainstream hardware. All of the hardware choices still collapse into deployment realities. Battery life, thermal limits, real-time response, and engineering complexity decide whether the design is actually usable. A chip is only useful if the system can survive on power, stay cool, and respond on time. The practical trade-off is how much complexity the team accepts in exchange for the efficiency gain. That is why embedded and edge roles value people who understand both models and hardware constraints. The important skill is knowing when an accelerator solves a real product problem and when it just adds expensive complexity. The right conclusion is a conditional one. Dense, continuous, power-constrained workloads can justify an accelerator, while modest or rapidly changing workloads are often better served by a simpler host. The final check is always the same. Match the hardware to the workload, the power envelope, and the integration cost. That is the lens you carry into the next hardware class, where specialization gets pushed even further. A good accelerator is not just fast. It fits the model family, the energy budget, and the path to production. When those pieces line up, it can make a product possible, and when they do not, the extra hardware is just added complexity. Hardware choices become central when a workload needs tighter latency, lower power, or more reliable real-time behavior than general-purpose processors can provide. The rest of this part compares two common paths: reconfigurable hardware and fixed-function silicon. Those limits are physical, not just computational. A design can be accurate on paper and still fail in the field if it drains the battery, misses a timing window, or overheats the device. That trade makes sense when the workload is stable and the shipment volume is high enough to justify the effort. The gain comes from shaping the hardware around one job instead of asking a general chip to cover everything. The main reason is mismatch. The product needs something the usual chip cannot deliver efficiently enough. The next few points show how that pressure builds and why hardware specialization enters the discussion. A team often starts with a development board because it is the fastest way to test the idea. The prototype may function, but one narrow operation becomes the bottleneck, where the power budget gets used up long before the target battery life is reached. A CPU or accelerator may already run the model. The real question is whether it can meet the latency, power, and throughput the product requires. Custom hardware enters when ordinary compute stops being the right fit for those constraints. FPGAs sit in the middle of the design space. They behave like custom hardware, but they stay changeable after fabrication. That makes them useful when the circuit needs to be shaped carefully without committing to a permanent chip design. The logic inside an FPGA can be programmed to act like a chosen digital circuit. That gives engineers a way to build hardware acceleration, test it, and revise it without manufacturing a new chip each time. The language changes the thinking. In Verilog or VHDL, the goal is to describe circuits, timing, and signal flow, not to write step-by-step software instructions. That flexibility matters in edge AI because many designs are still in motion when the hardware work begins. An FPGA can hold space for experimentation, for narrow acceleration, and for cases where the data path or precision target may still change. A voice-trigger device on a tiny battery is a good test case. An FPGA can handle filtering, feature extraction, or a compact inference path while the rest of the system stays asleep, which can turn a barely feasible design into one worth field testing. ASICs go one step further and lock the design into the chip itself. That fixed behavior is expensive to create, but it can be excellent when the workload is known and the efficiency target is strict. After fabrication, there is no retargeting in the FPGA sense. The chip has to be designed, verified, and manufactured correctly the first time, because the result is what ships. That rigidity is why ASICs can win on performance per watt. It also means late requirement changes are painful, because a mistake can cost a great deal of time and money to fix. A fixed chip only pays off when the market is stable enough to justify the upfront work. If the design is still shifting, the commitment is too dangerous. The decision is economic as much as it is technical. The same logic can be sensible on an FPGA and reckless as an ASIC once volume, cost, and power targets are put into the same frame. Engineering trade-offs alone do not decide the answer. The amount of time, money, and shipped hardware all change which option is worth pursuing. An FPGA lets the team validate the idea much sooner because the hardware can be changed after the design is built. An ASIC takes far longer because the design and verification burden is much heavier. FPGA work is still serious engineering, but ASIC development brings in more specialized people, more verification, and a fabrication expense that is hard to ignore. At small shipment counts, the FPGA is easier to justify because the upfront cost is lower. At large scale, a custom chip can become much cheaper for each device that ships. A general-purpose processor wastes more energy on overhead, and an FPGA usually improves that, but a well-designed ASIC often goes further still. That is why fixed silicon becomes so attractive when the same task must run continuously at scale. The economic math changes with shipment volume. The fewer units you make, the harder it is to recover the chip design effort. The more units you make, the more that fixed investment starts to pay back. That is why the technical similarity can be misleading. Two designs may look close on paper, yet one is a good FPGA candidate, and the other is too costly to justify as an ASIC. A practical path usually starts broad, then narrows as the requirements become clearer. The example that follows shows how teams move from software-friendly hardware to specialized silicon in stages. A team usually begins with the fastest platform available, so it can test the detector and prove the product concept. If the device cannot meet battery life or latency targets there, the hardware plan has to change. An FPGA is the safer middle step because it can prove whether the workload maps well into hardware. It also gives direct measurements of what improves: power, latency, or both. Only after that does a fixed chip become a serious option. If the requirements keep shifting, the team keeps the FPGA path and preserves flexibility. If the numbers are stable and the scale is large, the ASIC can become the long-term answer. This kind of work sits in specialized engineering teams, often where power budgets are tight or shipment volumes are high. The skills are broad because the job spans digital logic, system design, and product constraints at the same time. People in these roles have to think across hardware design, thermal limits, system architecture, and manufacturing realities. The best work comes from seeing the full product, not just the circuit block. A working design is not enough. The real test is whether the system can be built reliably, shipped in the field, and supported without surprises. The practical rule is simple. Custom hardware is a response to limits, not a default choice. The final comparison below pulls together when flexibility still matters and when specialization starts to win. FPGAs are the bridge when the design still needs room to change. ASICs are the end point when a workload is mature, the volume is large, and efficiency matters more than flexibility. That is the decision rule to keep in mind. If the workload is still moving, stay flexible. If the workload is stable and the numbers are big enough, specialization can become the better engineering choice. Custom silicon matters when edge AI systems have to meet tight limits on power, latency, or throughput. The contrast between FPGAs and ASICs makes the trade-off between flexibility and efficiency very concrete. At that end of the spectrum, the hardware is tailored to one workload instead of many. That usually buys better efficiency and speed, but it also raises the cost of changing direction later. That is why teams resist jumping straight into custom hardware. A board or module can be revised, a fabricated chip cannot, so the workload has to be stable enough to justify the commitment. The image should separate the chip from everything around it. The goal is to show that the silicon sits inside a larger system, not by itself. A useful diagram makes the surrounding platform visible too. Memory, power regulation, connectors, and sometimes a host processor all shape what the chip can actually do in a real device. That framing keeps the lesson grounded in systems thinking. The important question is not only what the chip can do, but how it fits into the rest of the hardware. The board level is where all the supporting pieces live. Those parts decide how data arrives, how power is managed, and how the chip communicates with the outside world. The chip level is narrower and more focused. It carries out the specific computation, often in parallel and with much tighter control over timing than a general-purpose processor. That progression helps explain how products mature. Teams usually prove the idea on a development board first, then tighten the integration, and only later decide whether the workload justifies a custom chip. The reason is usually pressure from power, latency, and scale. When those constraints are severe, general-purpose hardware can stop being the best fit. A small edge node may need to run for months on very little energy, so every milliwatt matters. In that setting, wasted memory traffic and extra control logic become real costs, not minor details. That question is more practical than asking for a chip right away. If the answer is no, an FPGA often becomes the next step because it lets the team test a hardware-style design without committing to permanent silicon. FPGAs are the flexible side of custom hardware. They behave like real hardware in performance terms, but the logic can still be reconfigured after manufacture. That reprogrammability is what makes an FPGA valuable during development. It gives hardware-level behavior without forcing the team to freeze the design too early. The workflow looks more like circuit design than ordinary software writing. Engineers describe how signals move and synchronize, and the device is configured so the silicon itself implements that behavior. That flexibility is exactly why FPGAs show up so often first. They let a team test timing, reshape data paths, and adapt when a model or interface changes, even if the result is less efficient than a fixed chip. ASICs sit at the opposite end. The logic is locked into silicon, so the chip is optimized for one workload rather than made to adapt to many. That fixed design is what gives an ASIC its advantage. When the circuit matches the task closely, it can use less power, finish work faster, and move data more efficiently. The downside is rigidity. If the model changes or the product needs new features, the chip itself cannot change with it, so a new design cycle begins. That is why ASICs usually come later. They pay off when the product definition is mature, the workload is stable, and enough units will be shipped to recover the engineering cost. The economic logic changes as a product moves from experimentation to scale. Each stage values a different mix of learning speed, flexibility, and unit cost. A prototype is judged by how quickly it teaches the team something useful. The same hardware choice can look very different once the product is close to shipping. In early work, flexibility beats low unit cost. Teams often accept a pricier FPGA board because it shortens the feedback loop and reduces the chance of building the wrong design. A pilot run makes those hardware constraints more visible. An FPGA can still be the right fit when the volume is modest or the system is still changing, because it proves the architecture before any irreversible tape-out. At high volume, recurring cost starts to dominate. Then an ASIC can win because the upfront expense gets spread across many devices, but the risk rises sharply if the design is wrong. FPGAs are often the first custom hardware step because they reduce uncertainty. They let engineers prove the mapping from algorithm to hardware before deciding whether a fixed chip is justified. That early validation matters because it turns an abstract plan into a real implementation. If the FPGA works well, it becomes a reference point for what an eventual ASIC would need to achieve. A good chip can still fail as a product if the surrounding platform is awkward. Integration, manufacturing, support, and the rest of the board all have to work together for the system to succeed. The right choice is always tied to a real deployment. The Riverwatch example makes that practical trade-off easier to see. A low-power edge detector can work on a development board and still miss the final power budget. Moving to an FPGA keeps the parallel structure while letting the team reshape the data path and verify timing under real constraints. Only if the demand is large and the requirements stay stable does an ASIC become worth serious attention. If not, the FPGA can remain the better answer, even when it is not the most efficient chip on paper. The same split shows up in hiring. FPGA roles and ASIC roles overlap in systems thinking, but they live in different parts of the product and business landscape. FPGA work shows up where engineers need to shape data flow directly at the hardware level. ASIC work is concentrated in organizations with enough scale and resources to justify long, custom silicon programs. The decision becomes much simpler once the product constraints are clear. Flexibility wins early. Specialization wins only when the numbers and the workload support it. That distinction captures the whole story. FPGAs let engineers build hardware-like systems without freezing the design, while ASICs become efficient because they are locked to one job and can be optimized around it. When the workload is stable and the volume is high, ASICs can pay off. When uncertainty is still high or the shipment scale is smaller, FPGAs usually remain the more sensible path. Edge servers are server-class machines placed close to where data is created. That matters because the main idea is not a special hardware category, but a familiar server moved to the edge so it can act locally. This side of the edge stack keeps the full server model intact. The difference from cloud infrastructure is mostly where the machine sits, not how it is managed or what kind of workloads it can run. An edge server is usually the same kind of machine you would recognize in a data center or IT room. It is deployed near sensors, cameras, machines, or building systems so data does not have to travel far before it is processed. Because these are still servers, the normal administration tools still fit: remote access, patching, permissions, monitoring, backups, and virtualization. That makes them easier to adopt when a team already knows server operations well. Local AI can run on this hardware when it helps, but it is not required. When acceleration is needed, A GPU usually adds inference speed, while the machine remains a general-purpose server rather than a dedicated AI appliance. The reasons are practical. Keep sensitive data local, cut response time, reduce network traffic, and fit into existing site operations. Those pressures are what make edge deployment worth considering. Processing video or telemetry on-site reduces the need to ship raw data away. It also lets decisions happen quickly enough for real-world control tasks, while avoiding unnecessary backhaul across the network. These environments already have racks, switching, power, cooling, and staff who understand server-grade equipment. Local compute fits naturally there, especially when the organization wants direct control over the data. A production line makes the trade-off easy to see. The goal is fast local decisions on camera feeds, without depending on a distant cloud service for every frame. Cameras can watch for safety issues, part errors, or process deviations, and a nearby server can analyze that stream on site. That gives faster alerts and keeps sensitive footage inside the facility. That capability comes with real costs: space in a rack, cooling, and reliable power. A server is far more capable than a small device, but it also asks for the kind of infrastructure that a factory can support. A campus or building deployment follows the same pattern. One server can combine camera feeds, access logs, occupancy data, and environmental readings, then turn them into alerts or dashboards without pushing everything through the backhaul link. The boundary is set by physical constraints. Once power, heat, and footprint become tight, server-class hardware stops being the right fit, and smaller devices start to make more sense. A rack server needs space, electrical capacity, and thermal management. That rules out many field sensors and battery-powered nodes, where the hardware has to stay small and sip power for long periods. Bigger hardware usually buys more memory, storage, and expandability. The trade-off is that heat and power rise with it, so a smaller Linux SoC can be the better choice when a workload only needs light pre-processing or a narrow always-on classifier. The decision is not about which device is best in the abstract. It is about whether the job needs cloud-like capability on site and whether the location can support the power, space, and maintenance that come with it. These systems sit right between IT and operational technology. That means the people who run them often need familiar server skills rather than highly specialized embedded design skills. Systems administrators, infrastructure engineers, and deployment teams usually handle the practical work, provisioning hardware, hardening the operating system, managing updates, reading logs, keeping the network reachable, and responding when something fails. That familiarity lowers the barrier for organizations that already run servers well. A person who understands storage, networking, and basic GPU setup can contribute a lot, even without designing custom silicon or firmware. The clean mental model is simple. Treat edge servers as on-site servers that trade cloud distance for local control. Once that frame is clear, the deployment choices become much easier to judge. An edge server makes sense when an application needs serious compute close to the data source, especially when privacy, latency, or bandwidth are part of the requirement. It is a practical fit when standard IT management is still enough. That puts it between tiny sensor nodes and highly constrained embedded hardware. When the cloud is too slow or too exposed, the edge server is often the next place to move the workload. If the workload does not justify server scale power and space, the smaller Linux SoC class is the better fit. It sits below the edge server when the job needs less capability and more efficiency. Edge servers matter because they move serious compute closer to where data is created. The focus here is how they fit real systems, what they enable, and where their physical limits start to shape the design. The hardware itself is ordinary server equipment. The important change is where it lives. That shift in placement changes latency, privacy, and how the whole system is operated. An edge server is not a special chip or a tiny embedded board. It is regular server class hardware placed near the cameras, sensors, or machines it supports so data can be handled locally instead of traveling to a distant cloud region. That ownership and placement difference changes the job. Cloud systems are built around central service delivery, while edge systems are usually deployed for a specific site, so the organization can keep inference close to the source and keep sensitive data inside the boundary. Operationally, these machines behave like normal servers. The useful question is not what exotic form they take, but how they fit into standard IT practice while serving local devices. From the software side, the environment feels familiar. Linux or Windows Server, package management, patching, logging, authentication, and monitoring all still apply. If someone already knows server administration, most of the operating model already makes sense. That is why infrastructure teams like this model. The workload may be edge AI, but the machine is still managed as server infrastructure, which means you treat it as a reliable server close to the action rather than as a fragile embedded device. AI workloads fit because they benefit from sustained compute and from handling several data streams at once. Once GPUs are added, the same server can accelerate inference without changing the basic operating model. These systems are comfortable with long-running, memory-heavy tasks, which is exactly what many vision and sensor pipelines need. The key point is that the platform is still server-class compute, even when it is doing real-time local inference. That becomes especially useful when several devices need to be handled together. A factory or building can gather many feeds into one local machine, let it run the models, and use the results immediately without pushing every raw stream outward. The advantages come down to three practical constraints: speed, data control, and network cost. Each one matters more when the data source is fixed and the system must react quickly. The main benefits repeat across many deployments, and they're easy to remember because they map directly to common infrastructure problems. When a decision has to happen quickly, every trip to a remote cloud adds delay. Keeping compute on-site shortens the feedback loop, which is often the difference between a timely response and a late one. Some organizations cannot let raw video, audio, or process data leave the premises freely. Local processing keeps that data closer to the source and reduces how many places it has to travel through. Bandwidth is the third pressure point. If a system can classify, aggregate, or summarize locally, only the useful results need to move onward, which is far cheaper and more practical than streaming everything. That is why these systems show up so often in fixed sites with clear boundaries. In those places, the edge server becomes the local processing hub instead of a distant dependency. The limits are not abstract design problems. They're about space, power, and cooling. That physical reality is what decides whether a server belongs on-site at all. These machines need rack space, electrical capacity, and cooling, and they're often noisy enough to require deliberate placement. That makes them a poor choice when the deployment has to be small, portable, or battery-powered. A basement, control room, or secure cabinet can support that kind of hardware. A remote field sensor or a fence post usually cannot, because the infrastructure simply is not there. That is the real design decision. If the site can support a full server and the workload benefits from centralizing many streams, an edge server fits well. If the job is smaller, a compact Linux SoC or gateway is often the better trade-off in power, size, and deployment effort. A concrete deployment makes the trade-offs easier to see. The same architectural choice can look ideal in one site and overbuilt in another, depending on the local constraints. In a factory, several cameras and sensors can feed one local inference server that watches the line, raises alerts, and keeps raw data inside the facility. That gives the operations team faster responses, less bandwidth use, and a cleaner privacy posture. That plan only works when the site can actually host the machine. If the facility cannot provide the power, cooling, or secure placement, the design has to move to smaller local hardware or to a gateway that does lighter preprocessing. The same logic applies in offices, hospitals, and campus security systems. Local analytics can satisfy policy and compliance requirements while still giving enough compute to handle many cameras or sensors together. The decision comes down to whether the site needs cloud-like compute at the edge and can physically support it. That boundary separates a full server deployment from something smaller and more distributed. An edge server is the most cloud-like option available at the edge. It is a strong choice when the workload needs serious compute on-site, but its size and energy use make it a specialized tool rather than the default answer. For real deployments, the job is not just model work. It also requires knowing networking, storage, hardware sizing, and when a system should stay local or be split across smaller devices. When the box feels too big, the next question is not how to shrink that same box. The better question is which smaller platform can still meet the workload, and that is where SOCs, gateways, and distributed device designs come into play. Multi-device edge systems split sensing, processing, and cloud handoff across several cooperating parts. The important idea is that each device does the job it is best suited to do, instead of forcing one box to handle everything. A sensor can capture data, a nearby processor can filter it, and another device can make the local decision. The point is to place each step where it fits best, so raw data does not always have to travel all the way to the cloud. That division of labor is what makes the architecture work. A gateway can collect streams, a local processor can watch continuously, and cloud services can stay reserved for summaries, logs, or rare escalations after the edge has already done the first pass. The gateway pattern shows up whenever many small devices need one stronger place to combine their data. It matters because the gateway can add compute, memory, and context that individual sensors usually do not have. Low-power sensors are good at measurement, but not at expensive analysis. A gateway sits in the middle, gathers their streams, and uses its extra resources to make a better local decision. A fleet monitoring setup makes the trade-off clear. The pallet nodes only need to report simple readings, while the truck gateway sees the whole load, spots patterns across pallets, and decides whether one of them needs attention. That split is often the best design choice, not a compromise. Limited battery life, intermittent networks, sensitive data, and old interfaces all push the work outward across multiple devices. The same idea also appears inside a single product. Different processors can take different roles, and the value comes from specialization rather than from treating every chip the same way. One processor may stay focused on always-on sensing, while another handles application logic, speech, graphics, or networking. The hardware may look like one device from the outside, but the internal workload is split by function. That split is useful when a system has a quiet mode and an active mode. One part keeps watch with very little power, and another wakes only when there is enough evidence to justify heavier work. A smart speaker follows that pattern well. A low-power chip listens for the wake word. A stronger processor confirms the request and manages the device, and cloud services come in only after the local trigger has been accepted. The question now is why raw data should not always go straight to the cloud. The answer is that local work often saves bandwidth, cuts latency, lowers false triggers, and improves privacy at the same time. If every stream is forwarded unchanged, the system pays for unnecessary traffic and slow responses. Filtering near the source trims the data, confirmation suppresses noise, and aggregation makes the fleet easier to manage. That is why Edge AI is usually partitioned rather than merely shrunk down. Each layer handles the part of the job that matches its constraints, from feature extraction to local decisions to long-term storage and retraining. The diagram for this section shows both versions of the same idea. In one path, the gateway forwards selected results. In the other, the device confirms locally before anything reaches the cloud, but the roles stay the same. The real design task is deciding where each piece of the workload belongs. That choice depends on power, scale, latency, privacy, and the infrastructure that already exists. For embedded AI and IoT products, the hard question is not whether a model can run at the edge. The hard question is which device should detect, which should confirm, and which should be reserved for auditing, retraining, or exceptional cases. A multi-device design can look complicated at first, but is often the cleanest answer to the real constraints. The architecture follows the trade-offs, not the other way around. The concrete examples that follow make this split easy to recognize in real deployments. Look for the handoff points between sensors, local processors, gateways, and cloud services, because that is where the architecture is doing its main work. Multi-device edge AI starts with a simple idea. The sensor device does not have to do everything itself. The point of this part is to show how work gets split across nodes, gateways, and cloud services when one box is not enough. A sensor hosting device often only captures the signal and does a small amount of filtering before passing the task onward. That handoff matters because the first device is usually the one closest to the world and the most limited in power and memory. The device beside the sensor may be battery-powered, tiny, or expected to run for years without service. A nearby gateway can take on richer analysis because it has more energy, more storage, and more room for complex software, so distribution becomes a practical requirement. Fleet systems make the split very clear. Many small nodes collect local signals, and a gateway turns those small reports into a larger decision. That pattern shows why edge AI is often organized as layers rather than as a single processing point. Think of pallet tags, warehouse bins, or industrial assets carrying simple sensors. Each node only needs to measure and summarize its own local conditions, while the gateway compares many devices together, checks for anomalies, and looks for patterns across space and time. That extra layer matters because the gateway can compare one device against another and keep history long enough to spot trends. The node stays cheap and simple, while the gateway absorbs the complexity that would be too expensive to push onto every tiny unit. Once you think in chains, the architecture becomes easier to design. The local device gathers evidence, the gateway interprets it, and a larger service can step in only when the situation needs broader coordination. A low-power Riverwatch node fits that model well. It can watch continuously, send a compact event when something unusual happens, and leave the heavier classification work to a gateway, so the node remains practical for long deployments. The same split shows up inside a single device, not only across a fleet. Different processors can specialize in always-on sensing, richer application logic, and optional cloud processing, and that separation is what keeps the whole product responsive and efficient. A smart speaker is a good example. One low-power processor stays awake for wake word detection. Another runs the main application once the device is active, and a cloud service can handle more expensive speech processing after the device has already confirmed the interaction is intentional. That division is not just neat design. It is how teams manage trade-offs. Always-on work stays lightweight, heavier logic runs only when needed, and cloud services remain optional so power use, delay, and user experience stay in balance. Local confirmation is especially important because it prevents every sound from being sent upstream. The device listens for the trigger phrase first, filters out irrelevant audio, and only then opens the wider speech pipeline, which also gives a practical privacy benefit. Older equipment brings another reason to split work across devices. The challenge is often not replacing the machine, but adding intelligence beside it without disturbing the systems already in place. Factories, HVAC systems, and building controllers often cannot run modern inference directly. A gateway can sit beside them, translate older protocols, read existing signals, and add new analytics while the original equipment keeps doing its job. That makes integration as important as model quality. The system has to fit current workflows, respect legacy interfaces, and improve operations without forcing a full replacement of expensive hardware. The real question is when to split the workload and when not to. A few practical conditions usually tell you that a multi-device design is the better fit. When a deployment has tight limits on cost, power, scale, or compatibility, the architecture usually starts to separate into layers. The board below lists the signs that point toward that split. If the node has to be cheap or battery-friendly, it cannot carry the whole inference burden. That pushes heavier work onto another device and keeps the local hardware simple enough for long-term use. When many devices together reveal a pattern, a gateway becomes valuable. It can compare readings, align timing, and make sense of the larger picture in a way that one isolated node cannot. Keeping part of the processing local reduces how much raw data has to leave the device. That does not guarantee privacy by itself, but it does give the designer a way to limit exposure and send only what is needed. At larger scale, coordination becomes a problem on its own. A central layer can organize reports, detect patterns across sites, and keep the whole deployment consistent instead of leaving each unit isolated. Retrofit projects are common because existing equipment is often too valuable to remove. Adding an edge device beside it is usually the practical path when downtime is expensive or the original hardware still has useful life left. A split design also makes sense when one part of the job must react instantly and another part can be slower and more compute-heavy. Separate layers let each stage run at the speed and cost that suit its own task. Seen from that angle, multi-device architecture is a normal response to real constraints. The designer decides which layers should sense, which should filter, which should infer, which should aggregate, and which should hand off to a wider service when needed. That is the kind of reasoning employers look for in system design work. The important question is where each part of the workload should live based on cost, privacy, scale, and operational fit rather than on model accuracy alone. If that question is clear, the architecture usually becomes clear too. A good deployment falls into one of three shapes: a single device pipeline, a cooperative multi-device system, or a local plus cloud split. Hardware choices in edge AI start with the kind of data the device must process and the limits of the deployment. That connection between workload and device class is what makes the rest of the design decision sensible. A useful hardware choice comes from matching the job to the machine, not from chasing the fastest chip on paper. The goal is to find a class of device that can handle the input well enough under real constraints. That matching step saves a lot of wasted effort later. If you start from the data form, sensor readings, audio, images, or video, you can narrow the hardware options before you lock yourself into a design that cannot meet power, memory, or latency limits. A capability matrix is only a rough guide. It can tell you what is plausible, but real products in the same category often differ a lot in memory, tool support, and practical performance. The next question is more concrete. What kind of input does the hardware need to accept? Once that is clear, the workload becomes much easier to compare against the strengths of each device class. Most edge devices see a small set of data patterns again and again. Thinking in those patterns makes it easier to decide whether a controller, a signal processor, or a larger platform is the better fit. Slow sensor streams are usually the easiest class to handle because the data rate stays modest. A small device can often monitor those signals, extract a few features, and make a decision locally. Once the sampling rate rises, the device has to move and process much more data every second. That pushes harder on memory, bandwidth, and the efficiency of the inference pipeline. Audio sits in the middle for many edge systems. It is still a streaming signal, but the model has to respond fast enough to catch short patterns, so signal handling and pre-processing start to matter a lot. Small images are often workable on modest hardware because the visual load stays limited. The main task is usually to recognize or classify the frame rather than recover fine detail. As image size grows, the hardware has to carry more pixels through the pipeline. That means more memory pressure, more bandwidth use, and usually a stronger processor or accelerator. Video is usually the hardest common case because it combines large images with continuous timing demands. The device has to keep up with both frame size and frame rate, which quickly raises the bar for the whole system. A device that handles one kind of input comfortably may fail on another, even if both sound like simple edge tasks. The jump from sparse sensor data to dense audio or video can change the hardware requirement completely. A system like Riverwatch Node can be tuned very differently depending on the deployment. In one case, it does small local inference. In another, it only keeps a few useful features. And in a harder case, it sends work upstream to a gateway. The useful part of the matrix is not the label itself. It is the hint about what a class of hardware can support in practice, once the workload and deployment limits are both taken seriously. Those labels are coarse, but they still help if you read them carefully. They describe a level of fit, not a guarantee that every device in the category behaves the same way. Full support means the class is normally a reasonable home for that workload. It should work within the usual edge constraints without forcing severe compromises. Limited support means the workload can fit only if you reduce the problem. Smaller models, lower resolution, heavier pre-processing, or shorter time windows are often the trade-offs that make it possible. None means the match is poor enough that ordinary deployment conditions make it unrealistic. A prototype might still run, but that is very different from a dependable production setup. That distinction protects you from bad design decisions. A model can execute on a device and still be the wrong choice if memory, heat, power draw, or latency make the system unreliable. The broad device classes give the matrix its structure. Each one sits at a different point in the trade-off between size, efficiency, flexibility, and raw capacity. The progression runs from tiny controllers at one end to much larger systems at the other. That range is useful because it maps directly to how much data, compute, and thermal headroom the design can afford. Microcontrollers are the most constrained, so they're strongest when a workload is small and simple. Low-end parts are good for basic time series sensing, while higher-end ones can sometimes stretch into limited audio or simplified vision. Digital signal processors shine when the job is about filtering, transforming, or extracting features from signals. Their strength is efficiency on structured data, not broad general-purpose flexibility. System-on-chip platforms sit in a very practical middle ground. They often combine the pieces needed for sensing, memory movement, and inference, so they fit a wide range of edge designs. Accelerators make visual inference much more practical, but only when the workload matches what they are built to speed up. If the bottleneck is control logic or sensor fusion, an accelerator may help very little. FPGA and ASIC solutions can be extremely efficient for a specific target workload. The catch is that efficiency for one target does not mean broad fit for every model or every deployment style. Edge servers are often the safer option when the job becomes large or operationally complex. More power, memory, and thermal room give them flexibility that smaller devices simply do not have. Cloud systems bring a lot of raw capability, but that capability comes with dependence on the network. Once connectivity or response time becomes a concern, the architecture has to account for that dependence. A good contrast is audio versus video. Audio can often live comfortably on a DSP or a modest SoC, while video usually pushes the design toward a stronger platform or a split system that offloads part of the work. The matrix is useful, but it should never be treated as permanent truth. Device families evolve, and the real limits of a product can shift with memory size, libraries, tool chains, and module design. Two parts from the same family can behave very differently once you look past the headline spec. A demo board and a production module may also lead to very different answers for the same workload. That is the right way to use the table. It helps you eliminate poor fits early, but the final choice still depends on the actual device, the actual model, and the actual deployment. The real decision happens when workload and scale are considered together. Hardware choice only makes sense when it is tied to how the system will actually run in the field. A battery node, an always-on microphone, a camera pipeline, and a mixed enterprise system all ask for different hardware. The right class depends on how much data arrives, how fast it arrives, and where the heavy processing should happen. Hardware and algorithm design stay linked from the beginning. The device class sets the boundary for model size and speed, and the input form plus pre-processing budget determine what is feasible inside that boundary. That ordering matters in a system like Riverwatch node. Once the hardware is fixed, it becomes clear whether the node runs a compact classifier locally, sends events upstream, or hands richer inputs to a gateway. This same judgment shows up constantly in real edge AI work. Employers want people who can reason about fit and trade-offs, not just pick a platform by brand or by headline performance. The useful conversation crosses embedded systems, machine learning, and integration work. You have to ask what can run locally, what needs filtering first, what can be accelerated, what should move off device, and what belongs in the cloud. That habit matters more than memorizing vendor names. It shows that you can connect the hardware decision to the deployment outcome, which is the real engineering skill behind the matrix. The closing idea is simple. Hardware selection is a fit problem. Once you read the matrix as a guide to constraints rather than a fixed rule, the next design step becomes much more grounded. The matrix gives you a quick first pass across MCUs, DSPs, SOCs, accelerators, edge servers, and cloud systems. It is helpful because the categories differ in useful ways, but every category still hides a lot of product-to-product variation. That is the natural next layer. Once the hardware boundary is clear, the algorithm question becomes much sharper. Which model family fits the device and the deployment well enough to be worth building? Workload comes first when choosing edge hardware, because the data shape drives memory, latency, power, and compute needs. That shift in perspective is what turns a vague device comparison into an engineering decision. Time series, audio, images, and video stress a device in different ways, so the signal itself tells you what the hardware must handle. A tiny vibration sensor and a high frame rate camera may both live at the edge, but they ask for very different amounts of buffering, throughput, and decision speed. A device versus workload matrix gives a quick first pass through a messy design space. It helps narrow the options before anyone spends time debating the wrong class of hardware. At the start of an architecture discussion, you usually need a plausible direction, not a perfect answer. That kind of table can point you toward a microcontroller for a simple sensor task, a richer platform for always-on audio, or accelerated hardware for vision workloads, which is enough to start talking about feasibility and power budget. Those tiers describe practical fit under real constraints. Full means the workload is a reasonable match. Limited means it needs simplification or help from elsewhere. And none means the class is a poor deployment choice at the expected scale, latency, or reliability target. The meaning of each tier becomes clearer when you tie it to actual device classes and actual workloads. Once the examples get concrete, the matrix stops feeling abstract and starts acting like a planning tool. For thresholding, anomaly detection, or compact classification on sensor windows, a low-end MCU is often enough. Audio can fit too, but only when the pipeline stays narrow and the signal is pre-processed carefully. Once the input becomes continuous or the feature extraction grows, memory and timing start to dominate the design. A low-power sensing node can stay on an MCU for a long time if the job is a small local classifier. Add wakeware detection or a richer acoustic scene, and the hardware choice shifts because the always-on workload needs more buffering and more concurrent processing. Acceleration matters most when the workload is visual and the input rate starts pushing the limits of general-purpose compute. That is where the boundary can move noticeably for edge systems. Image processing often works frame by frame, so one input leads to one inference and one decision. As resolution rises or the model gets heavier, dedicated acceleration can make visual tasks much more practical, especially in setups like low-light monitoring where the camera and lighting conditions force the system to work harder. Video is harder because it is a stream, not a single frame. The whole pipeline matters at once. Ingest, pre-processing, inference, storage, and often transmission. So even with an accelerator, the system still has to deal with bandwidth and memory movement. Several hardware families can cover a wide range of workloads, but they reach that ability through very different trade-offs. The useful question is which one fits the job cleanly, not which one can force the job to run. That comparison spans compact embedded chips, specialized silicon, local compute pools, and remote infrastructure. Each option changes the balance between efficiency, flexibility, latency, and deployment cost. SOCs bundle useful pieces into a small, power-aware package and often bridge the gap between tiny devices and heavier systems. FPGA and ASIC designs can be extremely efficient for stable pipelines. Edge servers are easier to program when several devices share local compute, and cloud systems offer the widest range at the cost of proximity, latency, and dependence on connectivity. A gateway that collects data from multiple nodes shows how work can be split across stages. Local devices can filter or classify first. Then the gateway can consolidate events and pass only the important data onward. The architectural question is which hardware belongs to this workload at this scale. That framing forces the real constraints into view instead of treating capability as a yes or no label. A tiny model on a simple signal may stay on a low-end MCU, while a noisier or faster-moving signal may need more memory or a stronger processor. Visual workloads and pooled deployments push the choice again, sometimes toward accelerators, gateways, edge servers, or the cloud depending on latency, connectivity, and privacy needs. These tables are useful, but only as current references. Hardware lines change, memory limits move, and vendors add or remove features over time. So the table guides thinking without becoming a permanent rulebook. That makes the matrix useful in interviews, procurement talks, and architecture reviews, where you need to justify a first-pass choice clearly. Being able to explain why one workload belongs on an MCU, another needs stronger always-on hardware, and another should move to a gateway or server shows real system-level judgment. Hardware classes are tools with different balances of power, latency, programmability, and cost. The best choice is usually the least complex tool that still meets the requirement, with the understanding that the map of options changes faster than the product you eventually buy.